Night in the cosmos is vast and eternal, far beyond the limits of any world, beyond the reach of atmosphere or cloud. There is a silence unlike any other. In our mind's eye, we slip free of Earth's cradle and sail beyond the planets, beyond the reach of the sun's light and into interstellar space, where the sun is now just one more star behind us. Here, it is a silence not just of sound, but of movement and time, a tranquil stillness that stretches between distant stars. In this endless expanse, darkness is not mere absence, but a presence of its own, a gentle velvet black that cradles the galaxies. Countless pinpoints of light glimmer softly across the sky, each a distant sun beaming through the void. They seem motionless, suspended in a quiet ballet, their faint glow unchanged for millennia. Drifting through this boundless ocean of night, one senses both immensity and peace. The stars are scattered like shy lanterns on the horizon of infinity. Between them lies the deep interstellar dark, a gulf so empty and so pure that it almost feels alive in its stillness. Here, in the solitude of space, there is no up or down, no edge or center, only the soft panorama of eternity unfolding in every direction. The universe breathes in long, slow rhythms, imperceptible but profound. Galaxies, like distant islands of light, slowly spin their spiral arms amid the darkness. Yet from this vantage, everything appears calm and unhurried. Occasionally, a whisper of starlight glides past, perhaps the faint streak of a far-off comet or the subtle glow of a nebula hidden in the distance. These are gentle reminders that even in quiet, the cosmos is alive with wonders. But here and now, all is serene. The fabric of space-time itself seems to hum a lullaby, a low and ancient vibration that underlies the silence. It is as if the universe remembers its own beginning in this hush, carrying the memory of creation in the very void. In this silence, there is no weight, no sense of time passing. 1,000,000 years could be a moment. A single second could stretch into an epoch. All that exists is the now, the present darkness speckled with faraway light. And in that now, one can simply be, as the cosmos simply is, vast, mysterious, and quietly sublime. As the journey ventures deeper into this cosmic night, the familiar fades away. There remains only wonder, and the soft, eternal glow of distant stars to guide any wandering thoughts. Far from the crowded star fields of galaxies, there are immense stretches of space almost entirely devoid of light. We float into one such region now, a great cosmic void, an expanse of nearly pure nothingness. Here, over hundreds of millions of light years, one might find only a handful of galaxies scattered like lone sentinels. In this vast volume, where elsewhere there would be thousands of galaxies, there are only silence and shadows. The emptiness is profound. Starlight from the surrounding universe barely reaches this deep recess. The darkness here is even darker, if such a thing were possible. Drifting through the great void is like drifting through a boundless cavern, lit by only a few distant candles. One can travel for eons and see no new spark appear on the horizon of space. Occasionally, after tens of millions of light years of darkness, a faint smudge of light might emerge, a solitary galaxy or a small cluster of stars, isolated and alone. Imagine a lone galaxy adrift in this emptiness, a tiny island of light and matter, surrounded by a sea of pure night. Its stars continue to shine and orbit each other, as they always have, but beyond its edges lies a gulf so empty that those stars might as well be the only ones in existence. If one were living on a planet within that lonely galaxy, the night sky would be almost empty of neighbouring galaxies. Outside the confines of its own stars, there would be only blackness, with perhaps a few faint, hazy patches of light where distant galaxies reside far, far away. How vast and silent the skies would seem. No grand tapestry of thousands of galaxies, only darkness stretching out almost without end. It is a cosmic solitude difficult to fathom. Scientists have given this place a name, the Boötes Void, though names scarcely capture its haunting nature. It spans roughly 330 million light-years across, a volume so large it could contain dozens of Milky Ways, laid end to end, yet within it, only a few dozen galaxies have ever been found. By comparison, a region of that size in a typical part of the universe might hold tens of thousands of galaxies. How did such a tremendous nothingness come to be? This question lingers in the dark, like an echo with no source. Some think that perhaps smaller voids merged together as the universe evolved, joining into one great desert of stars. Others simply accept it as an accent of randomness, a place where cosmic fate dealt a nearly empty hand. In this abyssal expanse, one feels the scale of the cosmos in a new way. The void is not frightening, but profoundly peaceful, like a calm, empty ocean at night. Here, the universe shows us a different face. Not the glittering cities of galaxies clustered together, but the quiet countryside of creation, sparsely populated and enveloped in a gentle darkness. Yet even in this quietude, the void has its own subtle story. The few galaxies that dwell here are puzzles in themselves. How do they survive in such isolation? Do they hold clues in their ages or compositions that tell of when and how this great emptiness formed around them? These questions, soft and speculative, drift without answer in the cosmic night. For now, the great void simply is a majestic emptiness, an almost perfect silence in the symphony of the universe. It reminds us that not all of space is filled with stars and light. There are recesses where creation rests, where the galaxies thin out like fading echoes until only darkness remains. In this void, we sense the depth of cosmic loneliness, but also a strange serenity. After all, even nothingness has a story, written in what little lingers within it, and in the shape of what is absent. At the edges of this void, far beyond our immediate sight, the universe becomes rich with galaxies again, almost as if outlining the emptiness. These voids and the surrounding galactic walls form a vast cosmic web, a lattice of matter and void that spans the entire universe. In that grand design, the Boötes Void is a silent gulf between filaments where galaxies cluster. Its existence hints at the grander pattern of creation, matter drawn together in some places and almost completely absent in others. In the darkness of this enormous cavity, one can almost feel the delicate balance of forces that shaped the cosmos. Gravity drawing matter into luminous clusters and leaving tranquil voids in its wake. Leaving the stillness of the great void, we carry with us a heightened sensitivity for any hint of motion or sound. For a long while, there is nothing but the whisper of our own thoughts. Then, very gradually, it becomes apparent that the universe is not entirely silent after all. In the vast darkness beyond the void, subtle signs of activity begin to emerge. It is as if, after holding its breath, the cosmos lets out a faint sigh or a distant murmur. We attune our instruments, listening carefully in the darkness, and suddenly the quiet is punctuated by an unexpected signal. All across the darkness, the cosmos has secrets to share, some in flashes and whispers rather than grand scenes. Imagine, in the midst of that great cosmic silence, a sudden flicker of energy passing by. It is invisible to the eye, for it comes as a burst of radio waves, but it carries power and mystery. Without warning or fanfare, a fast radio burst streaks through the void. In the span of a millisecond, this burst releases more energy than an entire galaxy does in that same moment. For a brief instant, it outshines the combined radio glow of billions of stars. Then, just as abruptly, it is gone, racing onward through space. These fast radio bursts, or FRBs, arrive unpredictably from the distant reaches of the universe. They travel for billions of years, crossing enormous gulfs of space, and by the time they reach this corner of the cosmos, they are faint and fleeting, a tiny blip in the background of the sky. If no instrument is listening at the right time and in the right direction, they would pass by unnoticed. They last only a heartbeat of time, a few milliseconds, and yet within that moment, they carry the energy of a cosmic storm. One might imagine them as cosmic sparks, or the distant echo of a lightning strike in the darkness, so far away that only a brief flash is seen. What could create such intense, quick bursts of radio energy? That question hangs in the stillness after each burst. Some believe these bursts are born from the death throes of massive stars or the merging of exotic objects, like neutron stars. Others suspect hyperactive neutron stars, called magnetars, stars with magnetic fields trillions of times stronger than Earth's, suddenly releasing their pent-up energy in a blinding flash. And there are ideas even more fanciful. Perhaps some advanced cosmic civilization's stray signal, or a phenomenon from physics yet to be discovered. In truth, FRBs remain one of astronomy's great unsolved puzzles. Each time one is detected, it arrives without a clear map back to its source, just a direction in the sky and a rough distance. Many of them seem to originate in faraway galaxies, tiny points in the sky so distant that their light has travelled for eons to reach us. When a burst is caught, often the source fades back into obscurity, leaving only questions. Occasionally, a fast radio burst will repeat, flaring again from the same location after days or months of quiet. These repeating bursts deepen the mystery. Astronomers listen, hoping a pattern might emerge, a rhythm to the cosmic heartbeat that could give away its nature. Indeed, one repeating FRB was found to have a gentle, regular cycle, a span of active days followed by silence, like some distant beacon softly pulsing. Yet even with this clue, no one is certain what engine drives it. The universe whispers, but does not yet reveal its full story. This is not the first time the cosmos has surprised listeners with unexplained signals. In the late 1970s, a radio observatory picked up an unusual transmission from the stars, a strong narrowband radio signal that lasted just 72 seconds. It appeared once and never again. On the printout of the data, an astronomer scribbled "wow" beside the signal's sharp peak, giving this mystery its name. The wow signal. It came from the direction of Sagittarius, and for a moment it looked exactly like what one might expect from an intentional beacon, perhaps sent by another intelligence. But the silence that followed was deep and enduring. No repeat call ever came. To this day, the wow signal remains a singular enigma, tantalizing and unresolved. Was it a glitch, a harmonic of natural cosmic noise, or a brief hello from the unknown? The stars have kept that secret well. Even familiar celestial objects have fooled us before. When pulsars were first discovered, those rapidly blinking neutron stars, sending metronomic pulses of radio waves, they seemed so artificial that their discoverers humorously labelled the first detection LGM-1 for little green men. It turned out to be nature's doing, a star corpse, spinning and flashing like a cosmic lighthouse. Yet the lesson remained that the universe can speak in pulses and patterns we might not immediately understand. Fast radio bursts are far less regular than pulsars and far more powerful in their brief lives. They are like whispers compared to the steady song of a pulsar, whispers that shout only once, then fade. Between these dramatic moments, space itself hisses and crackles softly with more subtle radio sounds. The constant hum of background radiation fills the cosmos, a faint noise left over from the birth of the universe itself. It is as though the cosmos has a baseline melody, ever present, on top of which these rare bursts and signals are sudden high notes. Huge radio dishes stare into the dark for nights on end, straining to catch those high notes. Each time one is captured, it serves as a reminder of how much still lies beyond current understanding. Here in the quiet of the cosmic night, one might imagine these bursts not as random at all, but as part of a grander, hidden conversation. Perhaps stars and collapsed suns have their own language of radio pulses. A language humankind has only just begun to overhear. Or perhaps the universe is simply full of ephemeral fireworks, bursts of energy that bloom and die unseen, except for the chance alignment of a telescope and timing. Either way, the effect is mesmerizing. From utter silence, a quick hello of energy, then nothing once more. Once more there is only the deep stillness of space. After the flash of a fast radio burst has long passed, the darkness closes in again. It becomes just one more thread in the tapestry of cosmic mysteries. Somewhere out there, it happened. Some cosmic event so intense it sent tremors across the universe. And billions of years later, a faint echo of it was finally caught. The thought alone stirs a gentle awe. In the endless night, the cosmos occasionally winks with these secret, sudden lights, and though fleeting, they serve as reminders that the universe is not truly silent, but full of quiet surprises waiting to be found. After the last echoes of a burst fade, we return to listening silence. Beyond these fleeting flashes and whispers, the cosmos carries an even more pervasive murmur, a faint glow that fills all of space, a remnant from nearly the beginning of time. Deep as the darkness of space is, it is not completely black or empty of light. Even where no stars shine, a delicate afterglow permeates the cosmos. It is the cosmic microwave background, a faint whisper of the universe's own birth, filling space with a uniform, gentle warmth only a few degrees above absolute zero. This primal light, invisible to human eyes, is everywhere, wrapping the universe in an almost unchanging haze of microwaves. It is as if the sky itself still remembers the dawn of time, echoing a memory from nearly 14 billion years ago. For the most part, this background glow is astonishingly smooth and even, the same in every direction to just a few tiny fractions of a degree. But not perfectly so. If one could see it with sensitive eyes, they would notice faint patches where the temperature is slightly warmer or cooler, subtle speckles and swirls in the otherwise uniform canvas. These slight irregularities are the imprints of the earliest cosmic tremors, the seeds from which galaxies and clusters eventually grew. They are like the gentlest of ripples on a calm sea, remnants of sound waves and quantum fluctuations from the universe's infancy, stretched out over cosmic time. Among these tiny variations is one that stands out, a curious cold spot, larger and cooler than expected. In a map of the microwave background, this cold spot appears as a broad, faint blue patch, a region a bit cooler than its surroundings by a few 100 millionths of a degree. That difference is minuscule, imperceptible to any creature, detectable only by precise instruments. Yet it looms large on the map because of its size and coherence, spanning a region of sky dozens of times the width of the full moon. This cool patch is an anomaly. It's as though one part of the early universe's afterglow decided to take a slightly deeper breath of chill than the rest. What could have caused the cold spot? One idea is that this patch of sky might be looking through an immense supervoid, an enormous region of space with far fewer galaxies and less matter than average. If a beam of light from the Big Bang's afterglow travels through such a void on its way here, it might lose a bit of energy, arriving slightly cooler. The void would be like a vast empty canyon that the light must traverse, stretching the light's wavelength just a touch more and sapping some of its warmth. Indeed, surveys of galaxies in that direction have hinted at a scarcity of matter, a great cosmic void, hundreds of millions of light years across, that might lie in the foreground of the cold spot. Perhaps the cold spot is a shadow cast by that void upon the ancient light. Yet even a void might not fully explain the size and depth of this cold region. Some cosmologists have pondered exotic possibilities. Could it be a statistical fluke? A 1 in 100 chance event born from random variations? Possibly. The universe is vast, and even unlikely things may happen somewhere. Or could it be something truly profound, like a bruise from a collision with another universe long ago, when the universe was young and such interactions might have been possible? In theories that imagine our universe as one bubble in a foaming sea of universes, two bubbles bumping could leave cold or hot spots imprinted in their cosmic background lights. Some have whimsically wondered if the cold spot in the CMB could be one such bruise from another bubble universe nudging ours in the distant past, or possibly the puzzling observation that some distant galaxy clusters seem to drift in the same direction, a phenomenon dubbed the dark flow, could hint at a gravitational pull from something outside our cosmic bubble. It's an intriguing thought, albeit unproven. For now, the cold spot remains an enigma. Most lean toward the mundane explanation, a supervoid or chance alignment, while others keep the door open for stranger tales. In the meantime, it sits quietly in the cosmic microwave map a subtle irregularity in the nearly uniform baby picture of the cosmos. Gazing at that map is like gazing at a faded memory, mostly smooth, with just a few mottled spots. And one of those spots, the cold spot, serves as a reminder that even the earliest light of the universe holds secrets not yet fully deciphered. The cold spot isn't the only odd feature in this baby picture of the universe. There are hints that the microwave background is ever so slightly lopsided on the largest scales, one hemisphere of the sky averaging a touch warmer than the other. This hemispherical asymmetry is hard to explain with standard models and could simply be chance. And then there's the curious alignment of some of the biggest temperature fluctuations along a certain axis, playfully nicknamed the axis of evil by some scientists. These too might be random, but they entice the mind. Did something in the early universe imprint a preferred direction on these primordial ripples? Or are these patterns just statistical quirks in our one observable sample of a universe? With only one cosmos to observe, distinguishing serendipity from deep significance is challenging. The cold spot remains the standout curiosity. A few have proposed exotic explanations beyond a void. Perhaps a texture, a relic defect in space-time left from a phase transition in the young universe, like a faint scar on the sky. If such a thing exists, it would be a window into physics far beyond our current reach, hinting at new fields or forces active shortly after the Big Bang. So far, though, evidence doesn't clearly favour this. Simpler explanations hold sway, and the cold spot may yet be nothing more than an improbable fluke, a random cold patch in the otherwise smooth canvas of the CMB. Whatever its cause, the cold spot encourages us to keep questioning. It's a gentle reminder that even the afterglow of creation has subtleties and surprises. The universe, in its infancy, was not perfectly uniform. It had personality, little deviations that would later grow into galaxies and voids. The cold spot might just be one of those early quirks writ large. As we gaze at the map of the cosmic microwave background, mostly bland and uniform, our eyes can't help being drawn to that cool blemish. In the quiet language of temperature and density, the cosmos is telling us that the story of its birth has chapters we have yet to fully decipher. From these whispers of the early universe, we turn our attention back to the structures around us in the present cosmos. As we survey the galaxies around us, a different kind of mystery comes into focus, one of unseen mass shaping what we see. Not all of the cosmos's mysteries shine or burst with energy. Some lurk quietly in the dark, holding things together with unseen hands. Peer deep into the cosmic ocean, and it becomes clear that the stars and galaxies visible are only a small part of the whole. There is an invisible presence woven through and around galaxies, a hidden mass that neither emits nor reflects light. It has been called dark matter, not because it is evil or shadowy, but simply because it does not glow. It is transparent and invisible, yet its gravity betrays its existence. The evidence for this unseen matter emerged gradually, like subtle clues in a vast puzzle. In the outer reaches of spiral galaxies, stars orbit the galactic center at startling speeds. By rights, with the visible stars and gas alone, those outer stars should be moving more slowly, or even flying off into intergalactic space. But they do not. They whirl around as if anchored by the gravitational pull of far more mass than can be accounted for by the matter we observe. It is as though each galaxy is surrounded by a massive, unseen halo, a cocoon of gravity holding it intact. Without this hidden mass, galaxies would not spin in the manner they do. Something invisible provides the extra pull. In clusters of galaxies, too, this mystery appears. Galaxies orbit the common center of the cluster faster than expected, and hot gas between galaxies is held by more gravity than visible matter can supply. Decades ago, astronomers studying a distant cluster noticed that it behaved as if it had far more mass than the sum of its stars. They called this missing mass dark, and so the term dark matter took hold for whatever was providing that unaccounted gravitational glue. Today, dark matter is understood as a fundamental part of the cosmic tapestry. By the best estimates, it outweighs normal matter by a factor of about 5 to 1. For every ounce of atoms that blaze in stars or form planets and people, there are about 5 ounces of something else, something transparent and ghostly, spread through space. In the great cosmic web that stretches between galaxies, dark matter forms the very framework. It clumps into filaments and knots under its own gravity, and ordinary matter, like gas and dust, falls into those gravity wells to form galaxies and stars. The grand design of galaxies sprawling across the universe, with vast voids in between, is largely a creation of dark matter's guiding hand. Without it, the universe would look vastly different, perhaps more scattered and less structured, with fewer galaxies having formed at all. Yet, for all its influence, dark matter remains frustratingly elusive. It does not interact with light, so we cannot see it directly. It does not collide with atoms in any obvious way, so it drifts through ordinary matter as a phantom. Right now, billions of dark matter particles, if they are particles at all, might be coursing through the Earth and everything upon it, unnoticed, like a ghost wind moving through walls. Dark matter makes itself known only by its gravity, by the way it tugs on stars and subtly bends the fabric of space. Sometimes, when a massive cluster of galaxies lies in front of more distant galaxies, the background galaxies appear distorted into arcs and smeared shapes, a visual clue that there is a powerful gravitational lens at work. Those lenses often reveal more mass than the visible galaxies alone could provide, again whispering of dark matter's presence. One famous example occurred when 2 galaxy clusters collided in the distant past. As they passed through each other, their clouds of hot gas crashed and slowed down, like 2 crowds of people colliding. But the majority of the cluster's mass did not behave that way. Instead, something swept cleanly through without slowing. Most of the mass just kept moving, as if it were made of ghosts that don't feel any friction. Astronomers observing this cosmic collision saw the gas, which we can observe via X-rays, separated from the bulk of the mass, which is inferred via gravitational lensing. This was a dramatic confirmation. The bulk of each cluster's mass was invisible and barely interacted except through gravity. The scene, the aftermath of the bullet cluster collision, is like a cosmic ghost story made real. The visible matter was left behind like a snail's trail, and the invisible matter carried on its way. Through such observations, astronomers have come to trust that dark matter is real, even if they still do not know what it is actually made of. What could dark matter be then? The possibilities read like science fiction, yet they are serious scientific conjectures. Perhaps it is a new kind of elementary particle, something forged in the hot furnaces of the young universe that now permeates space. These particles might form an unseen sea around every galaxy, a sea through which everything drifts without ever sensing it. Or maybe dark matter is a multitude of black holes, tiny ones left over from the Big Bang, so numerous and small that they have not been detected individually. Most scientists lean toward the particle idea, a weakly interacting particle that fills every galaxy's halo. Experiments deep underground and far above the Earth are listening for the faintest whispers of dark matter collisions with ordinary atoms, hoping to catch a direct glimpse of this invisible mass. So far, these efforts have met only silence. Dark matter keeps its secret well. And so, the universe stands composed mostly of something we have never seen. It's a humbling and wondrous realization. The stars, the planets, the glowing nebulae, everything familiar and visible, is the minority. The majority of the matter in the cosmos is this dark, elusive substance. Yet if eyes could somehow see it, the night sky would appear very different. Enormous halos would envelop galaxies, gently shimmering with gravity's influence. Filaments of dim matter would stretch across millions of light years, linking clusters like hidden bridges. The serene darkness around galaxies would no longer be truly dark, but filled with the structure of this invisible scaffold. Though dark matter is inhumanly silent and invisible, its effect is everywhere. It allowed galaxies to form and cluster. It holds stars in their galactic orbits. It shapes the very largest structures in existence. In the cosmic night, it is the quiet architect of the universe's scaffolding, a silent partner to the luminous matter we can observe. The search for its identity continues, listening in that silence for any hint. Perhaps someday, humanity will discover what dark matter really is. For now, it remains an elegant enigma, pervasive yet hidden, powerful yet subtle, an invisible canvas upon which the stars paint their light. Having realized that much of the universe's matter is invisible, we find ourselves confronted by another cosmic imbalance on a more fundamental level. It is not about how much matter exists, but what type of matter won the primordial battle. In the cosmic balance of things, another deep mystery lies in what we do not see, the apparent absence of antimatter in the universe. When the cosmos was born in the Big Bang, theory dictates that matter and antimatter should have been created in equal abundance, paired opposites that annihilate upon contact, releasing pure energy. And yet, as we look around, nearly everything we observe is made of ordinary matter. The stars, the planets, the interstellar gas and dust, our own bodies, all consist of matter particles with scarcely a trace of their mirror opposites. Why is our universe not filled with equal parts matter and antimatter? This imbalance is an anomaly, written into the very fabric of existence. Antimatter is like a photographic negative of matter. For every type of particle, proton, electron, neutron, there exists an antiparticle, antiproton, positron, antineutron, with the same mass but opposite charge and magnetic properties. If a particle meets its antiparticle, they destroy each other in a flash of high-energy light. Such encounters happen routinely in particle accelerators and certain radioactive decays, but in the natural cosmos we find antimatter only in tiny quantities. For instance, in cosmic ray collisions or around some black holes where intense fields create pairs of particles and antiparticles. We do not see entire stars or galaxies made of antimatter. If we did, their boundaries with normal matter regions would be sites of tremendous annihilation gamma rays, a glaring glow we could hardly miss. The sky, however, is mostly quiet on that front. One possibility is that in the primordial universe, for reasons unknown, matter gained a slight edge over antimatter. Perhaps a tiny asymmetry in particle interactions that left a surplus of matter after all the rest annihilated away. That surplus became everything we now see. Many physicists suspect some subtle violation of symmetry in fundamental laws caused this, and experiments are ongoing to find the tiniest differences between matter and antimatter behavior, for instance, comparing the spectra of hydrogen and antihydrogen atoms, or examining the decays of particles and their antiparticles. It's a plausible answer, yet it still feels a bit like a cosmic coincidence that just enough matter was left to build a universe. Another, more speculative idea asks, could antimatter still exist in large clumps, segregated from the matter we know? Imagine entire pockets of the universe made of antimatter, anti-stars shining with anti-light, anti-galaxies populated by anti-atoms, perhaps even anti-forms of life. If such regions were isolated far from normal matter, they might endure for eons without annihilation fireworks to reveal their nature. They would look nearly identical to ordinary galaxies from afar, since antimatter produces the same kind of light as matter. How could we tell an antimatter galaxy apart? One hint might come from rare cosmic particles. If an antimatter star occasionally ejects an antihelium nucleus and it makes its way to Earth, our detectors could capture it. In recent years, an experiment aboard the International Space Station detected a few possible antihelium nuclei in the cosmic rays. Nothing confirmed yet, but tantalizing enough to suggest that a few anti-stars might lurk in our galaxy's depths. So far, no clear evidence of bulk antimatter regions has been found. If they exist, they may be incredibly distant or hidden behind vast voids. Or it may truly be that our observable patch of the universe is dominated by matter for fundamental reasons, and antimatter survives only in trace amounts. Either outcome teaches us something profound, either about an imbalance sewn into the laws of physics, or about the potential for symmetry on cosmic scales that we have yet to discover. In the meantime, the mystery of the missing antimatter remains. Every time we witness matter and antimatter being created in labs or particle showers, they appear together and vanish together. Yet the cosmos, as a whole, tipped the scales ever so slightly in favor of matter. It's a silent puzzle. You cannot see the missing antimatter, only the void where it should have been. Some theorists even wonder if there could be an anti-universe elsewhere, mirroring ours in every detail except charge. For now, these ideas are speculative. We search the sky for any clue, bursts of gamma rays that hint at distant annihilations, unusual cosmic particles that shouldn't exist. As we continue to scan the heavens, we keep in mind that the universe often finds a way to surprise us. Perhaps one day, a quiet corner of the cosmos will betray the glow of twin galaxies meeting, one of matter, one of antimatter, lighting up the darkness as they resolve an eons-old separation. Until then, the dominance of matter stands as one of the great unanswered questions of the cosmic story, an imbalance that has made our existence possible. The universe hides things in different ways. Sometimes, as with antimatter, it simply doesn't leave any for us to find. Other times, it hides matter in plain view by warping the images we see. Gravity itself becomes an artist, and space its canvas. Gravity's subtle warping of space creates some of the most enchanting illusions in the cosmos. Unseen mass can bend light, and even ordinary galaxies or clusters can act as lenses, creating visual marvels from background light. In the quiet depths of space, a massive galaxy, sitting in front of a more distant one, can transform the farther galaxy's image into arcs and smears. These are cosmic mirages, known as gravitational lenses. The intervening gravity bends the path of light like a glass lens would, only here the lens is the invisible curvature of space itself. Sometimes, if everything aligns just right, the distant object's light is stretched into a nearly perfect circle around the foreground mass, an ethereal ring of light called an Einstein ring. To an observer, it appears as a delicate halo hanging in space, a ghostly duplicate of a galaxy drawn into a loop. In other cases, the background object might appear multiple times. A single quasar, a bright beacon powered by a galaxy's central black hole, has been seen as 4 distinct points of light arranged in a cross, each one a lensed image of the same faraway quasar. It is like seeing one lantern, but finding 4 reflections of it in a hall of mirrors. Except the mirrors here are the fabric of space curved by gravity. These gravitational lenses are not only beautiful, they also serve as natural telescopes. The light from the distant galaxy is often magnified by the lensing effect, allowing astronomers to see objects that would otherwise remain too faint. In the soft glow of a lensed arc, we can discern details of galaxies billions of light years away, learning about their stars and gas as they were eons ago. Each lensed image is a time-twisted view, showing a galaxy from the ancient past, brought into focus by a chance alignment of matter in between. Gravitational lensing takes many forms. In 1919, during a solar eclipse, astronomers observed starlight being bent slightly by the sun's gravity, a tiny deflection that proved Einstein's theory of general relativity correct. That was a gentle form of lensing within our own solar system. On the other extreme, entire clusters of galaxies can act as massive lenses. Hubble Space Telescope images often show distant galaxies smeared into arcs encircling a closer cluster. Sometimes multiple arcs from different background sources intertwine, creating a visual record of all the warped paths light took through the gravitational maze. One particularly striking lens is nicknamed the Einstein cross. A single quasar appears as 4 identical points of light arranged in a cross shape around a foreground galaxy. Each point is the same quasar, seen along a different bent route through space. It is a cosmic mirage of startling symmetry. In another case, astronomers observed a distant supernova that had been lensed into several separate images. Over the years, they watched those images appear one by one, a time-delayed replay of the explosion caused by the different path lengths of the light. It was as though gravity allowed us to rewind and re-watch a star's death from multiple angles. There is also a more subtle gravitational lensing called microlensing. This occurs when a single star or planet passes in front of a background star, momentarily magnifying its light. In recent times, microlensing events have even revealed planets that were otherwise invisible, including planets freely floating in space without a host star, rogue planets, that betrayed their presence only by the brief brightenings of background stars as they drifted by. In this way, gravitational lensing not only paints beautiful pictures in the sky, but also helps us find hidden objects, from distant quasars to wandering worlds. In all these scenarios, it's as if gravity is nature's lens maker, crafting glassless telescopes out of mass itself. The more mass in play, and the more precise the alignment, the more fantastical the resulting images. By studying these distorted shapes and multiple images, scientists can map the otherwise invisible distribution of matter, including dark matter, in the lensing object. Thus, gravitational lensing is not just a pretty trick, it's a powerful tool to probe the unseen. It allows us to see the invisible by the way it bends light. Each arc or ring in the sky is a messenger, telling us how space is curved in that region. Listening to these messages has unveiled missing mass and distant galaxies we'd never detect otherwise. Gazing upon a gravitationally lensed galaxy, one might feel the subtle presence of the lensing mass, like an unseen hand warping the view. It's a gentle distortion, a funhouse mirror effect on the grandest scale, but one that reveals rather than conceals truth. In the darkness, these lensed images appear as if the universe itself has set up mirrors or lenses to reveal hidden views. They add to the dreamlike quality of the cosmos, where distance and perspective can play tricks on the eyes. But unlike an illusion, these images are very real, just bent. They confirm Einstein's profound insight that space and time are malleable. In this calm exploration of the night, gravitational lensing stands out as one of the more whimsical cosmic anomalies, one that delights as much as it enlightens. For in the gentle arcs of a gravitational mirage, one witnesses the universe's quiet ability to surprise, bending the very fabric of reality in the most literal way and revealing wonders that lie far beyond ordinary sight. While gravity can contort light and bind galaxies, we have also learned it is not the only force at play on cosmic scales. There is a counterpoint to gravity's pull, something mysterious that pushes, gently reshaping the fate of the universe. If dark matter is the universe's hidden scaffolding, dark energy is its invisible impetus to grow. While gravity works to pull matter together, something else works in opposition on the vastest scales, pushing the fabric of space outward. Over a century ago, when Einstein formulated general relativity, he included a term in his equations, a cosmological constant, to allow for a static universe. Little did anyone know that term, or something very much like it, would resurface as the key to understanding an astonishing observation made in the late 20th century. The expansion of the universe is speeding up. For decades, astronomers measured the universe's expansion by watching distant galaxies drift away. It was assumed that, like an explosion slowing down, the expansion should be decelerating over time, reined in by the pull of gravity from matter. But when they looked carefully at far-off exploding stars, supernovae serving as standard beacons, they found those distant galaxies were dimmer than expected, not because the light was fading, but because the galaxies were farther away than they should have been if the expansion were slowing. The only explanation was that the expansion had been accelerating, like a car picking up speed instead of coasting to a stop. This was a complete surprise. Something was pushing the universe apart, counteracting gravity on cosmic scales. That something was dubbed dark energy. It is termed energy because it seems to be a property of space itself, an inherent push present even in the emptiest vacuum. As space expands, it doesn't thin out this energy. Rather, more space means more of this repulsive effect. In the simplest explanation, dark energy could be the reappearance of Einstein's cosmological constant, a subtle pressure embedded in space-time. Alternatively, it could be a new field, or exotic, dynamical energy permeating the cosmos, sometimes poetically called quintessence. But labels aside, what's evident is that dark energy now dominates the cosmic ledger. About 70% of the total energy content of the universe is in this mysterious form. Dark matter makes up most of the rest, and ordinary matter, the stuff of stars and people, is less than 5%. In an ironic twist, the substance humanity knows best is the rarest, and the unknowns rule the cosmos. The effect of dark energy is gentle to the point of being imperceptible in daily life, or even within galaxies. It doesn't rip apart solar systems or push stars apart within a galaxy. Gravity and other forces easily overwhelm it on those scales. But across the distances between galaxies, the cumulative effect is momentous. Over billions of light years, dark energy's push adds up, driving galaxies away from each other faster and faster. The cosmic expansion is like a vast breath that never fully exhaled. After an initial rapid inflation and a long, slow expansion, now it draws things apart ever more briskly. What does an accelerating universe look like in the far future? If dark energy remains constant, distant galaxies will continue to rush away. In tens of billions of years, galaxies outside our local group might recede beyond the horizon of visibility, their light stretched beyond recognition, leaving our night skies emptier. The universe would become a quieter place on the grandest scale, with each cluster or group of galaxies increasingly isolated in its own island universe. Yet this fate is a slow and silent one. Eons will pass, while the stars within our local cosmic neighborhood continue to shine and evolve. There is no abrupt end, just a gradual dimming of the cosmos as the gulf between star cities widens. Dark energy remains one of the deepest mysteries in cosmology. We can measure its effects with exquisite precision, mapping how it has influenced the growth of structures and the expansion history of the universe. But its true nature eludes us. Is it truly constant, an unchanging property of space? Or will it morph with time, waxing or waning, and perhaps changing the fate of the cosmos? Some theories suggest it might eventually weaken and even reverse, leading to a contraction, while others propose it might grow so strong in a far distant epoch that it rips even atoms apart, a hypothetical Big Rip. These speculations only underline how little is understood about this cosmic force. Lately, astronomers have encountered a subtle puzzle in their measurements. The universe's expansion rate, when calculated from the cosmic microwave background and the early light of distant galaxies, doesn't quite match the rate measured using nearby stars and supernova. This Hubble tension might be a sign of unknown nuances in our cosmological model. Perhaps dark energy's influence changed slightly over time, or some new effect is at play. It's as if the cosmos, in breathing outward, did so with a slightly different rhythm in its youth than it does now. For now, it remains a gentle enigma, a reminder that even in an era of precision cosmology, some mysteries linger quietly between the data points. In the vast, airless void, where one would assume nothing at all exists, there is something, the latent energy of space, quiet but relentless. The idea that empty space itself seethes with this repellent effect is quite poetic. Dark energy doesn't produce a sound or a flash. It won't cause objects to move nearby. It reveals itself only in the grandest scales, an almost spiritual presence shaping the destiny of the cosmos. It reminds us of an ancient notion that stillness can hide unseen forces. As we continue to observe distant supernovae and map the structure of space, we are listening to a cosmic heartbeat, the pulse of dark energy, even if we don't yet understand what drives it. Under the meditative sky, the notion of dark energy adds a layer of profound wonder. The universe is not only vast and old, it is changing in a grand, slow dance of expansion. Every galaxy, like a drifting ember from some ancient fire, is being gently carried outward by a swell of space itself. There is something both melancholy and beautiful in this vision, worlds moving apart in the endless night, yet each still shining in whatever company of stars remains to it. And all of it orchestrated by a force barely comprehended, an ever-present hush that drives the cosmos outward. In the tranquility of the cosmic night, dark energy is the silent hymn of space, a reminder that even in stillness there can be unseen motion, and even in emptiness there can be the energy of creation at work. Yet even as this acceleration reigns on the largest scales, gravity holds sway in our local patch of the universe. Even as the cosmos expands, our Milky Way is bound in a dance with its neighbours. Gravity continues its local dance, pulling galaxies into groups and clusters. One intriguing example of gravity's grip is the motion of our own galaxy and its companions. The Milky Way, along with the Andromeda Galaxy and thousands of other galaxies in our broader vicinity, is being gently tugged toward a particular patch of sky. This mysterious region lies behind the thick plain of the Milky Way's own stars and dust, making it hard to observe directly. Yet its pull is unmistakable. Astronomers call it the Great Attractor, a gravitational anomaly that seems to be drawing them in. The Great Attractor is not a single object, but rather a region of immense mass concentration. Likely a nexus of galaxies and clusters forming a supercluster. Located roughly 200 million light-years away, in the direction of the constellations Centaurus and Norma, it influences the motion of galaxies over a remarkable span of space. Our entire local group of galaxies, and the larger Virgo cluster beyond, are moving at hundreds of kilometers per second toward this hidden mass. The full cause isn't seen directly. Much of it is obscured by the Milky Way's foreground, but its presence is inferred from the pattern of galaxy motions. It's as if the galaxies are boats drifting on a calm sea, yet feeling the faint but persistent pull of a distant, unseen tide. Over time, studies revealed that the Great Attractor is only part of an even larger structure. Beyond it lies an even more massive concentration of galaxies known as the Shapley supercluster, which might be the true heavyweight pulling our entire region, Great Attractor and all, further in that direction. Our region resides in a complex web of gravitational influences. Our galaxy orbits within the local group. The local group falls toward the Virgo cluster. The cluster moves toward the Great Attractor, and that whole region may be falling into the even larger Shapley concentration. Each layer is like a nested current in the cosmic ocean, drawing smaller scales into larger flows. The motion towards the Great Attractor is subtle on human timescales. It will take billions of years for these motions to significantly alter our cosmic landscape. And in that time, dark energy's expansion will also be at work, potentially counteracting or diluting these motions over extreme distances. Perhaps gravity will win within our local supercluster, pulling everything into a denser cosmic city of galaxies, while beyond that, dark energy ensures other such cities recede forever out of reach. In the meantime, the Great Attractor remains an intriguing clue, that even in the age of accelerating expansion, gravity still weaves local stories. Floating here and now, one would never notice this motion. The night sky of stars is entirely governed by our own galaxy. The pull toward Centaurus is detectable only in sensitive measurements of galaxy Doppler shifts and in the slight dipole pattern in the cosmic microwave background that reveals our motion. It's a silent drift, a voyage without a sensation of movement, carrying our galaxy and countless others toward a destiny still concealed. The Great Attractor symbolizes how the universe, though expanding overall, still has eddies and currents. In the stillness of a galaxy's night, there is nonetheless a journey underway, a gentle, collective falling into an unseen gravity well. It's a comforting thought in a way. Even amidst the grand expansion, galaxies continue to gather and commune under gravity's guidance, forming ever larger families until the very largest scales are reached. The region of the Great Attractor was long hard to study directly. It lies in what astronomers call the zone of avoidance, where the dense plane of our Milky Way blocks the view with stars and dust. Only in other wavelengths like X-rays and radio have we been able to peer through that fog. What emerged was the discovery of the Norma cluster, Abell 3627, a massive cluster of galaxies sitting right where the Great Attractor's pull seems centered. This cluster, along with several others nearby, forms a gravitational valley. Our local group and the Virgo cluster are like marbles rolling gently into that valley. And beyond it, the Shapley supercluster, a titanic collection of clusters over 500 million light-years away, adds its weight, possibly tugging the whole region, Great Attractor included, further in that direction. We actually sense our motion through space via the cosmic microwave background itself. As our local group streams toward the Great Attractor, it causes a slight Doppler effect in the CMB. In the direction of our motion, the background appears a tad warmer, and opposite that direction it's cooler, by only a few thousandths of a degree. This CMB dipole anisotropy is a signature of our 600 kilometers drift through space. Though we can't feel it, we are moving through the universe, headed towards something unseen. Every galaxy in the neighborhood shares this journey. In a few 100 million years, our local group will be closer to the Great Attractor's heart, perhaps merging with other groups along the way. Yet because the space between clusters is also stretching, thanks to dark energy, it's unclear how close we'll actually get. It's a race between cosmic attraction and cosmic expansion. For now, we see the influence of the Great Attractor, rather than a clear image of its source. It's like seeing leaves swirl in a gust, and deducing the presence of a whirlwind ahead that is otherwise invisible. That swirl is enough to tell us something massive lurks. In the grand stillness of intergalactic space, the only hint of our galaxy's cosmic voyage is that telltale anisotropy in the microwave background and the velocities of galaxies around us. It's a nearly silent motion, as if all the galaxies are drifting down a gentle slope together. When astronomers chart the positions of galaxies around the zone of avoidance, using infrared and X-ray eyes, they indeed find clusters rushing in that direction, affirming that something enormous resides there. It is a reminder that not all the big players of the cosmos are immediately obvious. Some lurk in the shadows of observation, known first by their influence rather than by any image. The Great Attractor's story is a lesson in humility. Sometimes effects are apparent long before their causes are fully understood. As we float in our corner of the universe, we feel the tug of a destination we cannot yet fully picture. It adds a sense of direction to the cosmos. Not only are things expanding outward, but on smaller scales. Our galaxy is also falling inward, towards a point of great gravity, like a traveller drawn toward the nearest warm fire, even as the night grows cold and dark. That gentle pull persists, and we ride it through the darkness, curious about where it leads. Even beyond our local supercluster, the cosmic web extends on unfathomable scales. Galaxies collect into immense walls and sheets bordering vast voids, forming patterns that span billions of light years. Now and then, astronomers discover structures so colossal they challenge our cosmological models. Great walls of galaxies and enormous groupings of quasars have been hinted at, almost too large to fit the uniformity we expect. If such giants are real, they might be relics of the universe's earliest stirring, imprints from when matter first clumped together. Or they could simply remind us that our maps are incomplete and much remains to chart. Either way, the image of the cosmic web, lacy filaments of matter, and enormous voids is one of breathtaking grandeur. It's as if the universe has a hidden architecture, discernible only when we step back far enough to see the whole tapestry. Now, stepping down from those colossal scales, we turn to galaxies themselves, the fundamental islands of stars in this cosmic ocean. Each galaxy has its own story and character, and within them, we find no shortage of oddities and surprises. Galaxies are the grand islands of stars in the universe, each with its own history and personality. While many follow familiar patterns, spirals, swirling in graceful disks, or ellipticals glowing as diffuse balls, some galaxies present puzzles and quirks that intrigue astronomers. They behave strangely, or possess unexpected properties, as if quietly rebelling against the norms of galaxy life. One such mystery emerged with the discovery of a faint, diffuse galaxy that appeared to contain almost no dark matter at all. This galaxy, as dim as a smudge of cloud, moves and rotates as if only the stars and gas within it are providing gravity, with little or no invisible mass. Given that most galaxies are dominated by massive halos of dark matter, finding one that isn't is like finding a floating soap bubble made of lead. It just shouldn't stay together, and yet it does. How could this be? Perhaps this ghostly galaxy formed from the debris of a cosmic collision, its dark matter stripped away by violent tides, leaving a feeble collection of stars that manage to remain bound by their own slight gravity. Or maybe it's a sign that there are exceptions in the cosmic rulebook. Special circumstances where normal matter can form a galaxy, mostly on its own. For now, this galaxy drifts through space quietly, a faint wisp that challenges conventional assumptions and invites new theories. Then there are galaxies that are striking in appearance. Consider the rare ring galaxies, cosmic ripples frozen in time. One of the most captivating is a lone ring of stars known as Hoag's object, a perfect circle of hot blue stars surrounding a spherical core of older yellow stars, with almost nothing connecting the two. It looks like a celestial eye staring across space, or a jeweled bracelet with a hidden gem at its center. Such ring galaxies likely form when one galaxy punches through the heart of another, like a stone dropped in a pond, sending out a circular ripple. The gravitational disturbance triggers a wave of star formation moving outward, leaving a luminous ring. The result is transient on cosmic timescales. Over hundreds of millions of years, the ring will dissipate or morph. But for now, we witness a cosmic structure, both beautiful and rare. Even more dramatic are interacting and colliding galaxies. In the vast emptiness, actual stellar collisions are exceedingly rare, but the graceful shapes of galaxies can be distorted and reshaped by their mutual gravities. Two spirals passing close might throw out long tidal tails of stars, stretching like taffy, Over time, those tails may curl and sparkle with newborn star clusters like beads on cosmic strings. In the antennae galaxies, for example, a pair of merging galaxies has flung out arcing swathes of stars that resemble insect antennae. Their cores are crashing together slowly, spurring frenetic starbirth amid roiling clouds of gas. Yet to human eyes, if one could watch this collision play out, it would appear almost frozen, changing only over eons, a slow-motion ballet of star cities merging into one. Sometimes collisions produce less chaotic forms. The Cartwheel Galaxy is a stunning example. Once a normal spiral, it likely had a smaller intruder galaxy plow through it. The impact created not a usual messy merger, but a symmetric ring and spokes like a wheel. The galaxy now has a bright ring for a rim and faint radial arms like spokes, truly resembling a cosmic cartwheel suspended in space. Though the violent event that made it is long over, the galaxy wears the mark of that encounter in its very shape. In time, the ring will likely fragment and the galaxy will settle into something more conventional, but at this moment in its life, it is a one-of-a-kind wonder. Other galaxies mystify with their sheer scale or activity. Among these is the class of giants. Enormous ellipticals at the centers of clusters, bloated by countless mergers, containing hundreds of billions of stars, yet often cold and dormant in terms of new star formation. One can also find the largest known galaxies like IC 1101, a swollen elliptical in a distant cluster with perhaps 100 trillion stars, 10 times the size of our Milky Way. Such leviathans sit like monarchs at the cluster centers, grown fat by cannibalizing smaller galaxies over billions of years. In contrast, there are tiny dwarf galaxies, densely packed with dark matter, where only a trickle of stars huddles within a massive invisible halo, opposite to the dark matter-deficient ghost galaxy. And there are galaxies that shoot out enormous jets from their cores, powered by supermassive black holes, devouring matter and spitting energy across intergalactic space. These active galaxies can outshine entire galaxies in radio or X-rays. Yet to the eye, they may look like a quiet starry ellipse, with a faint jet visible only in specialized images. The variety of galaxies is as wondrous as the diversity of life in a forest. Each anomaly, a ring, a missing component, an unexpected burst of activity, tells a story of something that happened to that galaxy. Through these oddities, it becomes clear that galaxies evolve and change through interactions and internal upheavals. In a serene corner of the cosmos, one galaxy might appear calmly rotating, while unbeknownst to casual sight, it hides a strange secret, perhaps a double core from an ancient merger, or a peculiar distribution of star ages, hinting at a close encounter long ago. In the stillness of cosmic night, these galactic peculiarities are subtle. Only careful observation reveals them, painting a picture of a universe where even the stately galaxies have their dramatic moments and eccentric characters. Colliding galaxies slowly coalesce, proving that even destructive events can lead to new forms and renewed creation, as gas clouds compress to birth new stars amid the wreckage. Galaxies with missing mass challenge the unseen foundations of cosmic structure. Ring galaxies and tidal tails showcase the artistry of gravity, weaving stars into transient designs. The discovery of massive galaxies and quasars in the early universe raises questions about how they grew up so fast. All these play out on timescales beyond human comprehension, yet frozen in the images we capture, they speak to a cosmos that is dynamic and ever surprising. Under the gentle glow of millions of stars, a galaxy may seem eternal and unchanging. But the anomalies we find are reminders that they too are part of nature's ongoing story. Each strange galaxy is a bookmark in that great cosmic tale, a signpost that something unexpected happened here. Moving onward through these wonders in peace, one can appreciate how much diversity and mystery reside in these vast collections of stars that grace the darkness. And amid the starlight of galaxies lie some of the darkest enigmas of all. In the centers of galaxies and scattered through space are objects so dense and powerful that they challenge our understanding of physics. The black holes. Among the strangest denizens of the universe are black holes, regions of space where gravity is so intense that nothing, not even light, can escape their grasp. These cosmic enigmas lurk in the hearts of many galaxies, including our own Milky Way, and also wander in isolation as remnants of massive stars. A black hole forms when matter is squeezed into an extremely small volume, such as when a giant star exhausts its fuel and collapses under its own weight. If the mass is great enough, the collapse continues until an invisible boundary forms, the event horizon, beyond which anything that falls is forever trapped. What lies inside a black hole defies our current understanding. According to general relativity, all the mass collapses to an infinitely dense point called a singularity. Space and time themselves are warped to extremes. We cannot see this heart of darkness. We can only observe a black hole indirectly by its influence on its surroundings. Gas and dust spiraling into a black hole form a whirling accretion disk that can heat up and blaze with X-rays before vanishing from view. Black holes in galactic centers can power quasars, incredibly bright beacons visible across the universe, as their voracious feeding produces jets of energy shooting outward at nearly light speed. Those jets, like cosmic searchlights, tell us a mighty black hole resides at the core. For a long time, black holes were purely theoretical. Now we have evidence of them in multiple ways. We have observed stars orbiting an unseen mass in the center of the Milky Way, whipping around a dark object of about 4 million solar masses, our galaxy's central black hole, serenely waiting in darkness. And in 2019, humanity saw the shadow of a black hole for the first time. A ring of glowing gas encircling a dark silhouette in the giant galaxy M87, captured by a global network of radio telescopes. That image confirmed these monsters are real, behaving as physics predicted. An eerie void where light is missing, outlined by a halo of light bent by intense gravity. In 2022, a similar effort unveiled the shadow of the black hole at our own galaxy's center, proving that even the Milky Way's placid core hides a dark heart. Black holes also announce themselves through gentle tremors of space-time. When two black holes collide and merge, they release energy in the form of gravitational waves, ripples in the fabric of space-time that spread outward like the faintest of whispers. In recent years, detectors on Earth have picked up these whispers from distant collisions as black holes a billion light-years away spiraled into each other. These events last only seconds, and the waves that reach us move the detector mirrors by less than the width of an atom. Yet, from that tiny signal, scientists confirmed the existence of merging black holes in the depths of space, proving once again how dynamic and strange our universe can be. Despite all we've learned, much about black holes remains mysterious. Do they obliterate information or somehow preserve it? Do they spawn new universes behind their horizons, as some speculative ideas suggest? Stephen Hawking predicted that black holes aren't completely black. They should slowly evaporate over immense timescales, leaking energy via what we now call Hawking radiation. If so, a black hole left alone will eventually fizzle away. Its mass radiated into the void over trillions upon trillions of years. None of this has been observed yet, as the timescales are far beyond human reach, but it paints a curious picture. Even black holes, the ultimate fortresses of gravity, might not last forever. Black holes also produce intense tidal forces. Near a small black hole, gravity increases so sharply over short distances that an object would be stretched vertically and compressed sideways, a fate whimsically known as spaghettification. For larger black holes, this effect is gentler until deep inside. Thus, falling into a black hole could be a bizarre demise. One might be torn into strands of atoms, all while an outside observer would never see the plunge complete. It's a mind-bending end, fitting for such mind-bending objects. In the cosmic landscape, black holes are like silent voids with a formidable presence. One could drift near a stellar mass black hole in a spaceship and see nothing out of the ordinary until getting perilously close. Then starlight would warp and a dark circular shadow would loom ahead, marking the beginning of forever. They are nature's deep wells, and once something falls in, it becomes part of that hidden interior, its details lost to the outside universe. And yet, from these invisible prisons come phenomena that light up the cosmos and stir our curiosity. Black holes teach us that where darkness and light meet, some of the universe's most profound secrets lie. Black holes bring us face to face with the malleability of space and time. As we contemplate their effects, we naturally begin to question the nature of time itself and how it can be stretched or stilled by the cosmos. Time is usually taken for granted as a steady flow, ticking uniformly everywhere. But in the cosmic realm, time itself can stretch and skew in surprising ways. Under the influence of immense gravity or great speed, the passage of time changes. It's not just a philosophical idea, but a measured reality of our universe, as predicted by Einstein's theories. This means that what one observer calls a second might be, for another observer, a longer span, depending on their circumstances. Deep in space, near the edge of a black hole, time can slow almost to a standstill compared to clocks far away. Consider a spacecraft venturing near a massive black hole, carefully orbiting just outside the point of no return. To the astronauts on board, time flows normally. They live, breathe, and count seconds as usual. But if they could return home, escaping the black hole's grip, they might find that eons have passed in their absence. A short excursion for them could correspond to centuries or millennia in the outside universe. This isn't science fiction. It's the natural outcome of gravity warping time. The stronger the gravity, the slower time runs relative to elsewhere. Thus, near a supermassive black hole's event horizon, where gravity is extreme, a clock would tick at a glacial pace from the perspective of a distant observer. Even without such dramatic journeys, we see hints of this effect. Precision clocks on Earth tick just a little slower than those in satellites orbiting above, because Earth's gravity slightly dilates time at its surface. In daily life, the difference is imperceptible, yet it must be accounted for in technologies like GPS to remain accurate. Scale that difference up to astrophysical levels, and truly strange scenarios emerge. If one could hover safely near a neutron star or black hole, one might witness the universe around speeding by. Stars would wheel overhead at an accelerated pace, and distant events would unfold more quickly relative to your own time. One would effectively be in slow motion, a spectator to the distant future. Conversely, from the vantage of distant space, anything falling into a black hole appears to slow down as it approaches the event horizon. If an object were to drop toward that abyss, an outside observer would see its motions gradually become sluggish, its clock seeming to nearly freeze. The falling object never quite appears to cross the horizon. It just fades and reddens, lingering at the edge of darkness. In reality, from the object's own perspective, it plunges through in finite time, meeting whatever fate awaits inside. But the outside universe will never witness that final moment. To the external world, time has nearly stopped for the doomed traveller. Speed, too, can twist time. A spaceship racing close to light speed would experience time more slowly relative to stationary observers. This is time dilation of special relativity. If such a ship embarked on a round-trip journey among the stars and returned, the crew might find they had aged only slightly, while decades or centuries passed on their home planet. This twin paradox scenario is a thought experiment that becomes very real if ever spacecraft travel fast enough. In a sense, high-speed travel is a form of one-way journey to the future. These distortions of time are subtle in ordinary settings, but near extreme cosmic objects they become profound. They illustrate that time is not an absolute backdrop, but part of the dynamic fabric of the cosmos. Just as space can bend and ripple, so too can time. Black holes, with their intense gravity, are like deep wells in that fabric, where time slows down. The edge of a black hole, the event horizon, is as much a horizon in time as in space. Beyond it, nothing can be seen, and from it, signals take effectively forever to climb out. It's humbling to consider that the familiar ticking of seconds is not universal. The cosmos has pockets where time itself flows differently. Imagine civilizations around a black hole, if such could exist. They might experience the universe at a different pace than those elsewhere. The concept stirs the imagination gently, highlighting how intertwined time is with space. In the calm of a starry night, these relativistic oddities are hidden. We look up and might assume time flows the same everywhere. But quietly, in distant gravitational fields, clocks tick to a slightly different beat. The universe holds time secrets. Places where one could, in theory, see far future epochs of the cosmos by dwelling deep in a gravity well, or preserve youth relative to the outside by travelling fast. These are extremes not easily reached, but they are real features of the physics that governs everything. Perhaps the exact mechanics matter less than the poetic idea. Time is elastic. The cosmos contains not only strange sights and sounds, but strange rhythms of time. And in a very distant future, time itself may play the final trick. Some cosmological models suggest time could stretch on infinitely as expansion continues, or that time might even loop or end in ways not yet understood. But here and now, under the eternal stars, it is enough to accept that time, like the cosmos, can hold surprises. Drifting in the present, one finds that what is present can depend on where and how one drifts. Such musings invite a peaceful awe. The universe's mysteries are not only in the arrangement of matter and energy, but in the flow of time that guides cosmic history. In the vast night, one can nearly feel the deep time of the universe, billions of years embedded in the silence. Yet those years might pass differently in another frame of reference. It is a quiet marvel. Time, so intimate to us, can dance to different tunes across the universe. And so, the cosmic night carries on, indifferent to our human clocks, weaving a tapestry where space and time intermingle in the grandest, most subtle ways. Our thoughts now drift back to the ultimate moment of time, the dawn of the universe. What happened in those first fleeting instants of existence? The cosmos guards that secret behind a veil our science is just beginning to lift. We have traced cosmic mysteries across space and time, but what about the mystery of the very beginning? The Big Bang Theory describes how the universe expanded from an extremely hot, dense state. Yet the exact moment of birth, time zero, remains shrouded in paradox. Our physics can roll back the expansion to fractions of a second after the Big Bang, but at some point, densities and energies become so high that our equations falter. We hit a singularity, a point of seeming infinite density, which is likely a sign that our understanding breaks down. What really happened at the first instant? Did time and space themselves emerge from nothing or from a prior existence? It's a question as profound as any. The ultimate anomaly, perhaps, that the universe exists at all. One idea that has helped answer some early universe puzzles is the theory of cosmic inflation. It proposes that a split second after the Big Bang, the universe underwent a stupendous exponential expansion, doubling in size over and over at a mind-boggling rate. In less than a trillionth of a second, it would have grown from subatomic to astronomically large. This burst of inflation can explain why the universe today is so uniform on large scales. Distant regions now far apart were once in close contact before inflation blew them apart, and why space is so nearly flat. Inflation would have stretched any initial curvature to near flatness. Inflation is an elegant fix, but it raises new questions of its own. What caused inflation to start and stop? What was the inflaton? A hypothesized field that drove it. Those remain mysteries. Inflation, if true, might also have sown the seeds of all cosmic structure. Quantum fluctuations, tiny random jitters in the fabric of space at the smallest scales, would be rapidly stretched during inflation to astronomical scales. These ripples became the density variations that later grew into galaxies and clusters. Thus, the pattern of galaxies we see today could be a direct imprint of quantum noise from the universe's first moment. It's a beautiful connection between the subatomic and the cosmic. We see evidence consistent with this idea in the cosmic microwave background's slight irregularities, which match what inflation predicts in broad strokes. Yet, because we cannot observe inflation happening directly, it remains somewhat speculative. Physicists are searching for a more definitive clue. For example, a particular swirl pattern in the polarization of the cosmic microwave background that inflation would have produced via primordial gravitational waves. A few years ago, there was excitement over a potential detection of this signal, but it turned out to be dust in our galaxy mimicking the effect. The true detection may still await more sensitive instruments, And then there's the question of before. If inflation happened, what came before it? Was there a prior universe that gave birth to ours? Some theories suggest a cyclic cosmos, where big bangs and big crunches happen over and over, or a collision of membranes in a higher dimensional space sparking new universes. Others suggest our Big Bang was a transition from a quantum nothingness to something, a fluctuation out of an empty void. All these ideas push to the edge of science, where it intertwines with philosophy. Standing here, figuratively, at the dawn of time, we are confronted with both darkness and light. We have light in the sense that we understand a great deal about the early universe after the first tiny fraction of a second, and we see its echo in the microwave background. But we face darkness in what lies at the very beginning, a horizon in time we have yet to cross. It is humbling that even as we map out billions of years of cosmic history, the very start of that history eludes us. Perhaps one day, a new theory of quantum gravity will illuminate this moment, or maybe it will always retain an element of the unknowable. In any case, the birth of the cosmos remains one of its greatest enduring enigmas, a reminder that some questions sit at the threshold of the observable and the imaginable, inviting us to wonder what the reality could be. Inflation's grand vision of multiple cosmic bubbles sparks a bold possibility. Perhaps our universe is not alone. Perhaps beyond the edge of what we can see, other universes bloom, each with its own story. Our journey through cosmic anomalies inevitably raises a grand question. Is our universe the only one, or just a single chapter in a far larger cosmic library? The idea of a multiverse, countless other universes existing beyond our own cosmic bubble, is speculative, yet it lingers at the fringes of cosmology. If true, it could provide context for some of the mysteries we see. Perhaps some anomalies are the subtle fingerprints of other universes brushing against ours. Or perhaps what we consider unusual might be commonplace in a broader ensemble of worlds. One motif of multiverse theory comes from the concept of eternal inflation. In that wild, split second after the Big Bang, our universe is thought to have expanded incredibly fast. Some theories suggest that inflation didn't end everywhere at once. While our regions stopped inflating and went on to form stars and galaxies, other regions might have continued to balloon and then stopped at different times, spawning distinct bubble universes. Each bubble would be a universe with possibly different properties, maybe different physical constants, different arrangements of matter, perhaps even different numbers of dimensions or laws. They would be separated from us by regions still inflating, effectively keeping them out of contact. Yet occasionally, just maybe, two bubble universes could collide or brush against each other, leaving faint imprints. We already mused that the cold spot might be one such imprint. It's intriguing to think that the largest bruise on our cosmic microwave sky could be a sign of another universe's existence. There are other multiverse notions too. Quantum physics hints that every random event might spawn multiple outcomes, each realized in its own branch of reality, a many-worlds interpretation where countless parallel timelines exist side by side. That idea is more abstract and philosophical, difficult to test with cosmic observations. Still, it stretches the imagination to picture that beyond the horizon of what we can see or even conceive, there may lie entirely separate realms of space-time as real as our own. each with their own stars and stories. If multiverses exist, by nature they are hard to detect. Some proposals in string theory even suggest a landscape of trillions of possible universes with different physical laws. Our reality being just one garden in an unimaginably vast cosmic landscape. We search indirectly, by examining whether certain fundamental constants in our universe seem finely tuned. If they do, one could argue many universes exist with varying constants, and we simply inhabit one that allowed galaxies and life to emerge. It's a subtle line of reasoning, not a proof, but it keeps the multiverse discussion alive. From a poetic standpoint, the multiverse idea adds an even more profound layer of mystery to everything. It means our entire vast universe, with all its billions of galaxies and wonders, could be just a drop in an ocean of universes. The anomalies we catalogue, a weird signal here, an empty void there, might be mere curiosities in one particular cosmic bubble. In another universe, physics might permit entirely different phenomena, strange forms of matter, or alternate notions of time. It is a realm of almost boundless possibility, teetering on the edge of science and philosophy. As we float in the darkness, contemplating this idea, it feels both humbling and freeing. Humbling because the scale of reality might be far beyond anything we can ever directly know. Freeing because it reminds us that the cosmos, or cosmoses, need not conform to our expectations. Whether or not we ever find evidence of a multiverse, the concept encourages a gentle openness of mind. The universe has surprised us before. Perhaps the greatest surprises lie beyond it. In this reflective silence, we acknowledge that our universe could be part of a greater pattern, a single page in an infinite story. And though we may never read the other pages, the thought of them fills us with wonder. Every now and then, we search for hints of those other pages. A strange cold spot, a curious motion in far-off galaxy clusters, the so-called dark flow. Perhaps these are subtle fingerprints of other universes on our own. Or perhaps not. The very act of considering a multiverse stretches our imagination and keeps us open to marvels we have yet to discover. Not all wanderers in the cosmos are stars or galaxies. Some are worlds cast adrift in eternal night. Picture a planet without a sun, a rogue planet roaming the interstellar depths on its own. Far from the warmth of any star, it drifts in quiet solitude. Its sky is black, punctuated only by the distant shine of stars that are not its own. No sunrise ever comes for this lonely world. Day and night do not exist in the usual sense. Only endless night, illuminated faintly by the far-off glow of the Milky Way. Such rogue planets are thought to be abundant, strewn throughout our galaxy, perhaps in the billions or more, like lost embers from the fires of star formation. They may have been born around stars and later ejected by gravitational tussles, or formed in isolation from collapsing gas clumps, too small to ignite fusion. Whatever their origin, they wander free, unbound. One could pass right through the outskirts of a solar system and slip away again, unnoticed in the dark. Without a star's light, these planets are nearly invisible. Cold, dark globes discernible only by the subtlest gravitational lensing or a faint heat signature if they still retain internal warmth. Picture one such planet up close. Perhaps it is a giant the size of Jupiter, with a thick atmosphere swirling in perpetual darkness. Or perhaps it is a rocky world, its surface frozen and still under the cold of endless night. If it has an atmosphere, Maybe a faint aurora dances at its poles, sparked by cosmic rays or the relic magnetic field of its youth. On the ground, if there were an observer, they might barely make out their surroundings under the feeble light of the galaxy, a monochrome landscape of shadows. The temperature might be just a few degrees above absolute zero, unless the planet has geothermal energy stirring from its core. And indeed, even in such black solitude, there can be a spark of warmth. A massive rogue planet, still cooling from its formation, could emit a soft infrared glow. A smaller, Earth-sized rogue might keep a warm heart through the slow decay of radioactive elements in its rocks, or through tidal heating if it carries a companion moon. Beneath a thick insulation of ice, there might even be a liquid ocean kept unfrozen by the planet's internal heat. A secret sea in which simple life could cling on, shielded from the frigid vacuum above. These possibilities turn a lonely scenario into one subtly hopeful. Even in the absence of starlight, a world might not be entirely barren. For the most part, however, a rogue planet's journey is silent and uneventful. Millions of years can pass without significant change. Perhaps it traverses the sparse shoals of a nebula now and then, or brushes through the outer comet cloud of a star system, stealing a few icy bodies into its own tiny entourage. But largely, it is alone, a solitary voyager. If it had memory, it might recall the star it once circled, now just one among many points of light behind it. But it moves forward endlessly, bound to no master, following the gentle contours of the galaxy's gravitational field. From afar, to an outside observer, with a keen telescope, it would be nothing more than a brief dimming of a star as it crossed in front, or a slight perturbation in the motions of objects it passes. These subtle signs are how astronomers have begun to detect a few such phantom worlds, usually when one drifts in front of a distant star, momentarily bending its light, a fleeting gravitational micro-lensing event, or through a faint whisper of heat still emanating from a young, cooling planet. These subtle detections confirm that such wandering planets exist, even if we cannot see them directly. Yet, for the rogue planet itself, the cosmos is a quiet backdrop. It sails on, indifferent to the glittering constellations that drift slowly by over eons. There is a poignant beauty in such an existence, a world unto itself, enveloped in perpetual night, forging its path among the stars. It exemplifies the vastness and solitude that space can hold. But it also shows the resilience of planetary life, how a planet can continue on, stable and self-contained, even when cast away from its parent star. In the serene darkness, a rogue planet is a poem of loneliness and perseverance, a speck of complex matter adrift in an ocean of void. It is a reminder that not all homes need sunshine. Some wander in shadow, and yet they persist. One can sense the depth of interstellar space all around as we drift in thought alongside this lonely planet. The nearest star is a distant beacon, its light scarcely touching the darkness here. The dim band of the Milky Way is the only hint of structure, a patchy glow toward one side of the sky, a map of home for those who know how to read it. The background radiance of the universe, the combined glow of countless far-off stars and galaxies, is the only illumination by which to navigate. And yet, despite the isolation, the rogue planet remains a part of the galaxy's story. It obeys the same gravity that governs stars. It maybe even passes through the spiral arms from time to time, like a ship quietly crossing deep ocean currents. Its voyage is a slow, endless glide. In the stillness, one might almost hear the faint whisper of cosmic wind, the sparse particles and fields brushing past it. In the extremely far future, even our own planetary system might cast off members. As the sun exhausts its fuel and loses mass, or if a close stellar encounter jostles the outer orbits, planets like Neptune or distant dwarf worlds could drift away, becoming rogues carrying the remnants of their atmospheres into the night. The galaxy may eventually be littered with these orphaned worlds, each carrying memories of the star that birthed it. Eventually, after billions of years, our rogue planet might encounter a new fate. Perhaps it will pass close to another star and be captured into a new solar system, finding a second chance at sunrise. Or it might continue forever, until the galaxy itself is altered beyond recognition. But at this moment, in our mind's eye, it simply drifts under the eternal night, a testament to the fact that even in emptiness, a small world can persist. The scene is peaceful and melancholy, but also quietly inspiring. In the grand darkness between stars, the rogue planet journeys on, carrying its own story through the ages, a solitary witness to the vast and silent universe. And beyond even these, further wonders glimmer in the distance, inviting us onward. Our exploration of deep space anomalies is not yet complete. We will drift further still, into the unknown, guided by the same calm curiosity as the cosmic night gently unfolds its endless secrets. And so, leaving behind the familiar constellations of our earlier journey, we drift further into the quiet depths of space. The cosmic ocean stretches endlessly ahead, its darkness softly aglow with distant starlight. In this vast silence, new wonders begin to reveal themselves. Our voyage continues without a sound, a slow, gentle odyssey among mysteries that lie between the stars and beyond the edges of known space. The boundaries between reality and imagination blur in the dim light of galaxies far away. Each moment brings us deeper, floating as if in a dream through the midnight expanse, open to whatever secrets the universe is willing to share. Far from the warmth of any sun, we sense something pulsing in the dark. A subtle flicker, a beacon flashing rhythmically against the cosmic night. We glide toward it through an interstellar haze, drawn by its steady heartbeat-like signal. Soon, the source emerges, a pulsar, one of the strangest remnants of a star's life. This collapsed star core spins with astonishing speed, sweeping beams of energy into space like the rotating light of a lighthouse. Each time a beam swings past our line of sight, we see a pulse, a blink in the darkness, regular as clockwork. It is a cosmic lighthouse on a grand scale, a tiny star corpse broadcasting a repeating hello into the void. In some cases, like the famous Crab pulsar in the Crab Nebula, this flashing beacon spins about 30 times each second, firing off beams from radio waves to gamma rays with each turn. We can imagine it embedded in the ghostly glow of its supernova remnant. Indeed, in the Crab Nebula, tendrils of glowing gas are being pushed and ruffled by the pulsar's wind, as if that shattered star is still influencing the nebula around it, like a beating heart, sending out waves. From a distance, we might even see subtle flickers in the nebula, synchronized with the pulsar's flashes. A cosmic strobe, illuminating the expanding debris of the long-ago explosion. When the first pulsar was discovered in 1967, its signal was so precise that the astronomers half-jokingly named it LGM-1 for Little Green Men 1. The idea that perhaps an alien civilization was sending out a beacon flickered through their minds, For what natural thing could blink so perfectly on time? Yet it was no artificial transmitter at all, but a rapidly spinning neutron star. The collapsed core left after a massive star explodes. In this state, matter has been squeezed to unimaginable density, protons and electrons crushed into neutrons. The pulsar before us may be only a couple of dozen kilometers across, about the size of a city, and yet it contains more mass than our sun. It spins hundreds of times per second, so fast that if you stood on its surface, an impossibility of course, you would be carried around at a significant fraction of the speed of light. The intensity of such rotation and the star's powerful magnetic field together create those sweeping beams of radiation. We marvel at the regularity, a beacon flashing for millions of years, a stellar metronome keeping time in the cosmos. Up close, the pulsar would be a truly alien scene. Around its equator, the surface blurs from the incredible spin. The gravity is so strong that on its surface, mountains, if they exist, would rise mere millimeters, any taller, and they would be crushed by the weight of the star's pull. An object or person near it would be stretched and flattened by gravity hundreds of billions of times stronger than Earth's. But from our gentle vantage, at a safe distance, we see only the peaceful blink, on and off, a child of a long-dead star still shining a light, however thin, into the darkness. Not all pulsars are equal. Some are even more extreme. We drift past one that has been spun up to dizzying speed by pulling in material from a companion star. This millisecond pulsar spins over 700 times a second. Its flashes so rapid they blur into a faint whir. Others have strong magnetic fields that twist and crack, releasing sudden bursts of high-energy light. These are magnetars, the most magnetic stars known. Only a few of the millions of neutron stars become magnetars, but those few are remarkable. Imagine a magnetic field so powerful that it could erase a credit card from hundreds of thousands of miles away, or distort the very atoms in your body. A magnetar's field is 1 trillion times stronger than Earth's own magnetic field, and when it shifts, it unleashes energy like a cosmic storm. For long periods, a magnetar might appear quiet, a heavy, ultra-dense sphere just 20 kilometers across, with a smooth surface of super-dense matter. But inside, its magnetic field builds tension. Then, like a stressed crystal suddenly fracturing, the magnetic field can realign in a violent snap. In that brief moment, a colossal burst of X-rays and gamma rays erupts from the star. We recall a famous event recorded by our instruments on Earth. In December 2004, a magnetar on the other side of the galaxy let loose a flare so intense that even from 50,000 light-years away, it briefly ionized Earth's upper atmosphere. In just 0.2 of a second, that distant magnetar released as much energy as our sun would in 300,000 years. Yet here in the silent void, such outbursts arrive without sound or fanfare, only a sudden flash of invisible light, a whisper of particles. We can imagine it. If we had been nearer, we would have seen a halo of energy expanding like an ephemeral shell around the star, a momentary aurora in the dark. We drift on, absorbing the tableau. Around us lie the ghosts of shattered stars. Each pulsar or magnetar is the core left behind when a massive star ended its life in a supernova. These neutron stars are scattered throughout our galaxy, like gravestones marking where brilliant suns once shone. Yet they are far from dead. They spin, they beam, they sometimes crackle with energy. They keep the memory of their progenitor stars alive in their rotations. Some rotate so steadily that for navigators of the galaxy, they could serve as cosmic clocks or GPS beacons. Indeed, one day human explorers may use pulsars to find their way through space, as these beacons are reliable and identifiable by their unique periods, like fingerprints of time. In fact, when humanity sent the Voyager spacecraft out of the solar system, we included a map of Earth's location, using pulsars as reference points. A cosmic address label drawn with those steady beats and positions. Such is the reliability of pulsars that we trust them to help guide alien intelligences to our home, if any ever find that golden record drifting through interstellar space. As we take a final look at the pulsar's rhythmic flashing, we feel a sense of strange comfort. Here is order emerging from cataclysm. A star's violent death, a supernova, produced this tiny spinning lighthouse that now ticks off the seconds of millennia, unaffected by the chaos that birthed it. In the great darkness, it is a steady heartbeat. Its existence speaks to the resilience of the cosmos. Even in destruction, there can be a kind of harmony. Leaving the pulsar behind, we traverse a stretch of interstellar space. The darkness between star remnants is vast and tranquil. Occasional glints of distant stars punctuate the void. In this gulf, we have time to reflect on what we've seen. A tiny spinning beacon born of catastrophe, now a steady metronome in the silence. As we drift onward, the faint pulse fades into nothingness behind us. Soon, ahead, we notice a different kind of stellar ghost emerging from the darkness. Dimmer, less furious, yet captivating in its quiet resilience. This will be a white dwarf, cradled by the tenuous shell of a planetary nebula glowing softly around it. Not every star's end is so extreme. Stars only a bit heavier than our Sun do not collapse into neutron stars. Instead, they shed their outer layers gently and leave behind a dense core that shines softly. We come upon such a sight now, a faint white dwarf star, the remains of a sun-like star that has quietly sloughed off its atmosphere. Around it, a diaphanous shell of glowing gas expands outward. The star's former outer layers, set aglow by the hot core. This is a planetary nebula, a final luminous halo marking the transition of a star into its twilight form. The white dwarf at the centre is small, about the size of Earth, yet it contains most of the original star's mass, often around half the mass of the Sun or more, compressed into a sphere only a few thousand miles across. Such matter is in a state called degenerate matter. The atoms are crushed so close that quantum forces keep them from collapsing further. The little star ember glows white hot from residual heat, though no fusion burns in its heart any longer. When stars with similar masses as our Sun run out of hydrogen fuel, fusion ceases in their cores. The star's core contracts and heats up, while the outer layers puff out into a red giant stage. In that bloated phase, the star's outer envelope becomes unstable and escapes, blown gently into space by stellar winds and pulsations. What remains is this hot core, now a white dwarf, illuminating the drifting cocoon of gas around it. These nebulae don't last long, maybe 10,000 years. Modern telescopes, like the James Webb Space Telescope, have actually caught stunning views of such scenes. For example, the Southern Ring Nebula, where a pinpoint of a white dwarf is clearly visible at the center of concentric, glowing shells of gas. In that image, we literally see the tiny ember lighting up the beautiful shroud it shed. We drift closer to observe the white dwarf's gentle light. It looks unassuming, a point of white in the center of a hazy, multicolored cloud. Yet it is incredibly dense. If one could scoop a teaspoon of its substance, it would weigh tons upon tons under Earth's gravity. For instance, one famous white dwarf, Sirius B, the companion to Sirius, the brightest star in our night sky, is as massive as the Sun, but packed into a volume not much larger than Earth. For billions of years, this stellar core will radiate its leftover heat into space, gradually cooling. White dwarfs are sometimes called cosmic embers, and appropriately so. Like coals after a fire, they glow for a very long time as they cool, fading ever so slowly. The one before us may have a surface temperature tens of thousands of degrees now, shining in blue-white brilliance, but with no new source of energy, it will eventually dim. In time unimaginable, trillions of years, a white dwarf will cool to become a black dwarf, cold and dark. But the universe is not yet old enough for any to have reached that final state. Every white dwarf ever formed is still glowing, however faintly. As we watch, the expanding nebula around this white dwarf reveals delicate structures, streaks and filaments of neon and hydrogen glow red and green. Perhaps it formed shapes like overlapping rings or shells. Each planetary nebula has its own form. Some are spherical bubbles. Others form butterfly-like lobes or ghostly hourglass shapes. The pattern often comes from how the star shed its layers, sometimes impulses or jets directed by magnetic fields or companion stars. It's a beautiful farewell gesture of a sun, persisting only for a brief time on cosmic scales, maybe 10 or 20,000 years, before the gas disperses into the interstellar medium. Underneath that light show, the tiny central star will continue to shine alone as a white dwarf for eons. One fascinating fate of white dwarfs is that, as they cool, their material can crystallize. The carbon and oxygen in their core freeze into a solid lattice. In effect, the interior of an old white dwarf becomes a giant diamond-like crystal in space. Astronomers have identified white dwarfs that are in this phase of cooling, their insides turning to crystal. We imagine the core of our white dwarf solidifying, a trillion carat diamond hidden under its thin atmosphere of helium and hydrogen. It's poetic to think that the remnants of a star, like our sun, could end up as a gargantuan gemstone in the cosmos, shining faintly with leftover heat. Some white dwarfs have a more dramatic potential too. If a white dwarf orbits close to another star, it might steal matter from its companion, piling it onto its surface until a sudden thermonuclear flash occurs. A nova, a brilliant flare that can outshine an entire galaxy for a short time. Or if a white dwarf gains too much mass and exceeds a critical threshold, it can even detonate entirely in a Type Ia supernova, blasting itself to bits and forging heavy elements that seed the galaxy. But most white dwarfs will simply cool in peace, cosmic refugees of stellar evolution that slowly fade into the background. Reluctantly, we bid farewell to this stellar ember. Drifting away, the glow of its nebula dims behind us, fading like a gentle nightlight in the cosmic dark. We venture into a more sparsely populated region now, a calm interstellar expanse where only faint wisps of gas and the occasional distant star punctuate the darkness. Our journey takes us onward across several light years of emptiness, crossing from the scene of a star's end toward a realm of new beginnings. In the far distance, a gradual brightening in the cosmic haze signals that we are approaching a vast cloud of gas and dust. Ahead lies a tremendous stellar nursery, a place where the darkness is painted with subtle colours of creation. In a remote region between the stars, we enter a sprawling cloud of gas and dust, many light years wide. Starlight from young suns embedded within bathes the cloud's edges, making it glow in ethereal colours. This is a stellar nursery, a vast nebula where new stars are being born. The gas is mostly hydrogen, the prime material of the cosmos, mixed with cosmic dust grains that make the cloud appear dark and opaque in places. As we drift inside, we see great towers and pillars of denser gas, sculpted by radiation, and winds from massive newborn stars nearby. They stand like cloudy stalagmites, light years tall. These are akin to the famous pillars of creation in the Eagle Nebula, columns of creation where infant stars hide in their tips. We venture into one of these dense clumps in our imagination, letting the surrounding dust envelope us like a thick fog. Inside, we find a protostar, a warm, young star still gathering mass. It glows redly from its contracting heat, but its light is muffled by the cocoon. A swirling disk of gas and dust rotates around it. Within that disk, material is coalescing. Clumps that may one day become planets are forming in the shadows. Occasionally, a spark from the forming star's core sends ripples through the disk, but still fusion has not fully ignited. It's a stellar embryo, on the verge of stardom. Jets of material shoot out from its poles, carving paths through the surrounding cloud. These protostellar jets, like cosmic garden hoses, clear away excess dust along the rotation axis, allowing some of the hidden light to escape. Faint tendrils of nebulosity glow as these jets slam into the surrounding medium. It's a subtle light show, signaling the birth pangs of a star. Elsewhere in the nebula, we come upon a cluster of bright young stars that have recently emerged from their natal gas. They shine fiercely, their blue-white light flooding the cavern they carved out. The surrounding gas responds by fluorescing. Hydrogen emits a gentle rosy red glow. Ionized oxygen glows blue-green. Towering UV radiation from hefty O-type stars in the cluster is what excites these colours. Those massive stars are blazing fiercely and will burn through their fuel in just a few million years, a blink of an eye cosmically, likely ending their lives in supernova explosions that will stir and enrich this nebula even further. The whole vista is like an abstract watercolour painting spread across the heavens. We find ourselves in awe of the scale, knots and whirls of cloud, dozens of trillions of kilometres across, all illuminated by these tiny points of intense light. This cloud is turbulent and alive in its motions, yet enveloped in silence. Sound cannot carry in the near vacuum, so all this cosmic commotion unfolds in majestic quiet. We see evidence of the drama, but if we were truly here in person, we might be struck by the contrast. Brilliant light and dynamic shapes, but no sound at all, just an endless hush as new suns ignite. Star formation events are happening here and there, driven by gravity's inexorable pull, but we witness it in serene silence. There is a sweet fragrance of cosmic dust, at least in our imagination. Complex molecules formed on dust grains that will become ingredients for future planets or even life. As we wander through the nebula's luminous halls, we realize we are witnessing creation on a grand scale. Every star in the sky was once born in a place like this, Our own sun formed over 4.5 billion years ago in a similar stellar nursery, alongside sibling stars that have since drifted away. In that ancient nursery, just as here, some of the remaining dust and gas around the young sun likely flattened into a disk, the cradle of planets. Indeed, in this nebula, we can imagine around some of the fledgling stars there are protoplanetary disks, swirling pancakes of dust and gas, where planets will coalesce. Though we cannot see them with our eyes at this distance, our minds can picture them, dark disks silhouetted against the nebular glow, perhaps with bright rings or gaps carved by newborn planetary bodies. In a few million years this scene will evolve. Much of the glowing gas will dissipate, and a new open cluster of stars will emerge from the dispersing nebula, shining on their own. But for now, the nebula is still full of gas, cradling hundreds of infant stars in its diffuse embrace. We look towards a particularly radiant region. Maybe this is akin to the Orion Nebula, a stellar nursery visible even from Earth as a fuzzy patch in Orion's sword. In such regions, if we were truly there in person, the colours would likely be too faint for our eyes to perceive, as human vision needs long exposure to see the hues of nebula. But here, in our dreamlike exploration, the colours are vivid, and we can appreciate them fully. We see filaments of dark dust snaking in front of glowing backdrops, like ink-black veins in pink marble. We see brilliant points of starlight sparkling like newborn gems in a cosmic cloud. Despite the vigorous processes underway, there is a sense of serenity here. The timescales are so drawn out, the gestation of stars, the slow dispersion of the cloud, that to our perception it is a still, tranquil panorama. Birth is tumultuous, but it is drawn over tens of thousands of years, each moment a frame in a nearly static painting. Within this nebula, the temperature in many areas is just a few tens of degrees above absolute zero, cold enough that molecules can form. We drift by a region where the cloud is especially cold and dense, shielding itself from the nearby stellar glare. In this cold womb, molecules like carbon monoxide quietly emit infrared light. If we had infrared eyes, we would see parts of the nebula shining in longer wavelengths where these molecules radiate. These are the clues astronomers use to find stellar nurseries. The telltale glow of molecules, the dark silhouettes against richer star fields, the subtle infrared warmth of coalescing protostars. Eventually, we must take our leave of this celestial nursery. We float out of the glowing cloud, passing through its outskirts, where the light fades and the stars we saw born are now behind us. Around us, the sky grows darker again, with only the faint luminosity of the Milky Way's starfields to remind us of where we are. In this quieter region, just beyond the nebula, we reflect on the grand cycle we've witnessed. Star death, giving material for star birth. The ashes of old suns, becoming the cradle of new ones. A sense of the cosmic cycle settles in our thoughts. Not long ago, we saw the end of a star's life. A white dwarf and its planetary nebula. Here we witnessed the beginning. The gas and dust composing this nebula is not pristine. It is enriched with elements forged in earlier generations of stars. The calcium in the dust, the carbon, the iron. Those were cooked in stellar furnaces or in supernovae and then dispersed into space. Now they are coming together again to form new suns and worlds. The universe recycles itself. From death comes rebirth, over and over. Our own bodies contain atoms from ancient stars, and in this nebula, future stars are gathering the material that someday might become new solar systems, perhaps new life-bearing worlds. The nebula extends far beyond our sight, a tapestry of creation. We could linger here for ages, watching new suns wink into existence. But beyond the soft glow of these nurseries, the cosmos holds other phenomena, less visible, yet equally intriguing. As we leave the star-forming cloud, carrying with us the awe of witnessing starlight being kindled, we feel a gentle rain of invisible particles streaming through space. This is the backdrop of high-energy cosmic rays and other radiation that permeates the galaxy. Our path now takes us out of the pastel radiance of the nebula and into the nearly pitch-black space between stars once again, where these ghostly travelers zip by silently. Out here, far from any star, space seems empty. Yet it is not truly void. There is a constant drizzle of high-energy particles threading through the cosmos. These are cosmic rays, charged particles, mostly protons or atomic nuclei, that have been accelerated to incredible speeds by violent events like supernova explosions or jets from active galaxies. They whiz through the galaxy and beyond, usually unseen and unfelt. At this moment, countless cosmic rays are passing through us. We cannot feel them. They are subatomic pinpricks that seldom interact. In the silence of space, they can, however, announce themselves in subtle ways. Astronauts beyond Earth's protective magnetic field sometimes report seeing random flashes of light in their eyes, even when closed, cosmic rays triggering sensations on their retinas. It's as if the universe itself occasionally etches a tiny spark onto our vision, a gentle reminder of these invisible travelers. Cosmic rays were discovered over a century ago, when early experiments found that an electroscope, a device to detect radiation, would keep discharging even when isolated from known radioactive sources. It was as if radiation was coming from above, and indeed it was, from space. They are a subtle presence, but one that ties us to distant corners of the galaxy. A cosmic ray detected in our detectors might have been launched by a supernova that occurred millions of years ago and thousands of light years away. In that sense, these particles are like messengers or nomads, carrying energy and information across vast distances. Most cosmic rays are not extremely energetic. They are comparable to, or a bit more energetic than particles produced in human accelerators. But now and then, nature produces something truly astonishing. In 1991, detectors in Utah recorded an ultra-high energy cosmic ray that was almost beyond belief. A single proton moving so fast, it carried the kinetic energy of a baseball traveling at highway speed. This one particle, later nicknamed the Oh My God particle, was racing at 99.99995% of the speed of light. In terms of energy, it was about 50 joules, which might not sound like much, but to pack that into one proton, an entity so small it's almost unfathomable, is extraordinary. If such a proton hit your body, you wouldn't notice a thing. Its energy would be dispersed harmlessly among atoms. Yet it represents a dramatic example of nature's accelerators, outdoing our largest machines. Scientists still ponder what could accelerate a particle to such speeds. Perhaps the collapse of a star into a black hole or neutron star, or collisions of cosmic ray particles with something even more energetic in intergalactic space. It remains a cosmic mystery, a testament to the extremes the universe can reach. We imagine these particles streaking by, normally invisible, but perhaps we give them a visual metaphor. Tiny shooting stars at microscopic scale, each one a herald from some distant cataclysm. Some come from exploded stars, others possibly from the vicinity of supermassive black holes at galactic centers. When they hit Earth's atmosphere, they can occasionally produce faint flashes of light in upper atmospheric molecules, or create isotopes like carbon-14 that get incorporated into living tissues, subtly connecting us to cosmic events. There are other forms of interstellar radiation too. For example, high-energy photons like gamma rays that travel across space, or the ubiquitous cosmic microwave background, which is the faint afterglow of the Big Bang, present everywhere as a cold radio hum. But cosmic rays have a special intrigue. They are matter traveling, not light. They are physical pieces of stars and galaxies on a journey. In a way, they blur the line between here and there. As you lie under the night sky, dozens of these particles pierce through you each second, harmlessly, silently, unceasingly. It's as if the universe is lightly touching us, a gentle drizzle from the storms of distant suns. Out here in interstellar space, away from Earth's protective blanket, the cosmic ray flux is higher. If one were on a voyage between stars, over long periods, cosmic rays would slowly damage cells or electronics. But in our ethereal exploration, we simply note their presence as part of the environment. Occasionally, we might envision a particularly energetic cosmic ray colliding with a stray atom in the interstellar medium in front of us, triggering a minuscule explosion of secondary particles, a reminder that even in emptiness, there is activity. As we absorb the notion of these traveling particles, we sense that the cosmos communicates in many ways, sometimes in the quiet language of particles and fields. The cosmic rays are like a background whisper. Yet there are also moments when the universe speaks in a shout, albeit a distant one. We now turn our attention to phenomena that, unlike the constant drizzle of cosmic rays, arrive as sudden bursts, intense flashes of energy that for a brief time can outshine entire galaxies. We venture now into the realm of gamma-ray bursts, the most powerful explosions known since the birth of the universe. Without warning, a flash of intense energy ignites the darkness ahead. For a few heartbeats, an invisible blaze of gamma rays sweeps through space. We have encountered a gamma-ray burst, GRB, one of the universe's most powerful fireworks. It arrives with no advance notice, a sudden surge of photons at the highest energies. In those brief seconds, the burst unleashes a mind-boggling amount of energy, often as much as our sun will emit over its entire 10 billion year lifetime, compressed into mere moments. Then, as abruptly as it came, the flash fades. An afterglow may linger in lower energy light, X-rays, then visible light, then radio waves, like the cooling embers of an enormous explosion. But the initial burst itself is over almost as soon as it began. What could create such a titanic outpouring of energy? Astronomers have determined that gamma-ray bursts are associated with the deaths of stars and the collisions of ultra-dense objects. One type, the long-duration GRBs, likely occur when a very massive star, much larger than the Sun, reaches the end of its life, runs out of nuclear fuel, and collapses into a black hole. In that violent collapse, jets of material are blown out at nearly light speed from the star's poles, blasting through the star's outer layers and into space, producing an intense beam of gamma rays. If one of those jets is directed towards us, we observe a gamma-ray burst. Another type, short-duration GRBs, seems to arise from the merger of two neutron stars, or a neutron star with a black hole, a cataclysmic collision that also creates jets of gamma radiation for a brief moment. In both cases, what we are witnessing is a kind of cosmic birth through destruction, the birth of a black hole or a hypercompact object, announced by a stupendous flash. We recall that gamma-ray bursts were first detected in the late 1960s by satellites watching for nuclear bomb tests. To the surprise of scientists, they found flashes of gamma rays coming from space, not Earth. Decades of investigation revealed the extragalactic nature of most GRBs. They typically lie in distant galaxies billions of light years away. That is fortunate for us. Were one of these explosions to happen in our own galaxy and beam toward Earth from close range, it could have serious effects on our atmosphere. But in the vast majority of cases, these events are so far away that they pose no threat. They are simply spectacular light shows we observe with our instruments. Let us imagine witnessing a gamma-ray burst from a safe vantage. We wouldn't see the gamma rays with human eyes, but suppose we have a sort of cosmic all-sight. In the distance, a pinpoint of light suddenly surges in brilliance. For a brief instant, it outshines its entire host galaxy. The illumination might cast stark shadows even across interstellar space, if one were close enough. On Earth, we normally learn of these bursts through satellites. But remarkably, one burst in 2008 was so intense, it was briefly visible to the naked eye, despite its source being halfway across the observable universe. For about half a minute, a ghostly pinpoint of light from that explosion could be seen by human eyes, a breathtaking testament to the power unleashed. Then it's gone. If we hurried closer, at superluminal speed in our imagination, we would find at the burst's origin a scene of aftermath. A rapidly expanding fireball of hot plasma, racing outward at nearly the speed of light. That is the jet material, now cooling and interacting with the surrounding environment. It will shine in X-rays and then visible light for days or weeks as it expands and dissipates. Eventually, it will fade below detectability, leaving perhaps a newborn black hole and a remnant nebula enriched with heavy elements forged in the explosion. In fact, these gamma-ray bursts are one of the sources of the universe's heaviest elements. In a neutron star merger, for example, the collision can create gold, platinum, and other heavy atoms in huge quantities, which then scatter into space. Thus, the gold in a ring on someone's finger might have been forged in a cosmic flash like this, eons before the sun formed. It's humbling to realize that such brief, distant events can influence the material out of which future stars, planets, and even life are made. Floating here after the burst, the darkness returns to its normal state. The space around us is calm and silent again, as if nothing ever happened. Only our detectors, or memories, would know that a tremendous explosion just swept by. Because these bursts are so transient and far-flung, one could wander the galaxy for a lifetime and never be in the path of one. They are the definition of rare and fleeting. Yet they remind us that the universe still has its occasional convulsions, moments when energy floods out in overwhelming abundance, making even supernovae, ordinary star explosions, seem pale by comparison. And they stretch our imagination about what nature can do. We feel gratitude that our cosmic neighborhood is presently quiet. These outbursts, though ferocious, mostly play out at safe distances. We can enjoy the knowledge of them without fear, like watching lightning through a distant window. The burst we witnessed fades into memory. We find ourselves again in calm darkness, the drama concluded. It's almost hard to believe that such violence can be tucked away in the universe's far corners, while the rest of space remains so tranquil. After taking a moment to appreciate the quiet and let our senses recover from the imagined brilliance, we decide to turn from these intense, observable wonders to some stranger possibilities. Now our journey takes a turn from the realm of observed phenomena to the domain of the speculative and theoretical. We have seen some of the universe's grandest fireworks. Now we contemplate some of its most curious possibilities. Ideas that challenge our understanding of space and time. Ahead of us lies the idea of tunnels through space-time and other exotic cosmic architectures that might exist in theory, even if we have yet to find evidence of them. The gentle darkness beckons us onward, inviting us to explore not just what is, but what might be. In the quiet intervals between the spectacular events we've witnessed, one can't help but wonder, are there hidden pathways or structures in the cosmos that we haven't yet seen? The laws of physics, as we know them, allow some strange possibilities. One famous idea is the wormhole, essentially a tunnel through space-time, a shortcut connecting two distant points. Imagine bending a sheet of paper representing space so that two far-apart dots touch. A wormhole would be like a pinhole poked through the paper, linking those dots directly. In principle, Einstein's general theory of relativity has solutions that describe such tunnels, often visualized as connecting two black holes or two universes. We drift in contemplation, picturing what a wormhole might look like if it could exist in a traversable form. Perhaps from the outside, it might resemble a sphere or whirlpool of warped light, somewhat like a black hole's appearance, but instead of a dead end, it could be a throat leading elsewhere. No evidence for wormholes has been found, and most scientists suspect that if nature does make them, they might exist only at the subatomic scale, or for extremely brief moments before collapsing. They might require exotic forms of matter with negative energy to stabilize them, which we aren't sure exist in large quantities. Yet the allure of the concept remains. In the mind's eye, we toy with the scenario, stepping into a dark portal in one location and instantly emerging in another galaxy entirely, or perhaps in a different universe altogether. Science fiction has long spun tales of such travel, but underlying those tales is a kernel of scientific possibility. The universe, with its curved space-time, does not outright forbid wormholes. It only makes them very difficult to create or maintain. In our reverie, we gently float around an imagined wormhole mouth. It's a speculative scene. Perhaps the space around it shimmers from intense gravity. If we peer in, do we see a distorted view of the far end? Does the light from the other side come through as a foggy tunnel vision of an alien sky? It's fun to imagine. But then the vision fades. Whether wormholes are real or not, they remind us that space itself can be more malleable and strange than it appears. Other theoretical cosmic structures have been proposed, especially when scientists consider the infant universe. In those first fractions of a second after the Big Bang, as the universe expanded and cooled, it's thought that various phase transitions might have occurred, analogous to water freezing or steam condensing, but with fundamental forces and fields. If so, there could have been imperfections or cracks formed in the fabric of the young cosmos. One idea is cosmic strings, not strings like in string theory, but literally string-like defects in space, extremely thin, thinner than an atom, but incredibly dense and long, perhaps stretched across entire light years. A cosmic string, if one existed, would gravitationally pull on nearby matter and could even bend light, acting as a kind of cosmic optical fiber or gravitational lens that produces double images of distant galaxies. Astronomers have searched for the telltale signs of cosmic strings in sky surveys, like unexplained double images or slight irregularities in the cosmic microwave background. But so far, none have been confirmed. If a cosmic string passed through our region, we might not see it directly, but we'd notice its gravitational effects. For instance, we might see the stars behind it appear strangely duplicated, or their light bent into rings. Another hypothetical structure is the domain wall, a two-dimensional sheet-like defect that could separate regions of space with different vacuum states, different versions of physical laws that might have emerged in the early universe. A domain wall is a bit like a cosmic membrane. One side of its space has one set of properties, the other side has another. If a domain wall swept through our solar system, it could, in theory, fundamentally alter the physics here, something you definitely wouldn't miss. Fortunately, if such walls exist, none seem to be anywhere nearby, and theories suggest our universe either has none or they were annihilated early on. These ideas sound fanciful, but they arise naturally from thinking about how the early cosmos might have evolved with symmetries breaking and phases changing. To date, we have not found concrete evidence of cosmic strings or domain walls. If they do exist, they may be exceedingly rare or subtle. Still, searching for them encourages us to examine the universe at the largest scales for patterns or anomalies. In fact, when scientists mapped out the cosmic microwave background, the faint afterglow of the Big Bang that fills all of space, they did find something unexpected, an unusual alignment in the large-scale fluctuations of that background radiation, a pattern that shouldn't be there according to the simple cosmological models. This has been whimsically dubbed the axis of evil anomaly by some researchers. The name is tongue-in-cheek, meant to signify its troublesome implications for standard theory. It refers to the observation that the hot and cold spots of the microwave background, on the biggest scales, seem to line up along a particular axis across the sky, which oddly is roughly aligned with the plane of our solar system. It's as if there were a preferred direction in space, something cosmologists aren't comfortable with, since our theories assume no special directions. Isotropy. Could this be a sign of some cosmic structure or imprint? Perhaps from something like a domain wall, or just a strange fluke? Or is it simply a statistical coincidence, an alignment born of chance in a finite sample of random fluctuations? The debate about this axis continues. Data from the Planck satellite in 2013 found that the anomaly did not disappear. The alignment persisted, to the dismay or delight of theorists. Some have proposed that maybe our local motion or local structures contaminated the data. Others have gotten creative, suggesting new physics might be at play. Even ideas as exotic as a rotating universe or influences from beyond our observable realm. For now, the axis of evil remains a curiosity, not a confirmed revolution in cosmology. Most lean towards it being a curious fluke, or something explainable by yet unknown systematics. But the door remains open a crack. It's a reminder that even in the apparently uniform glow of the cosmic background, subtle patterns might hint at layers of meaning we've yet to decipher. As we float in the darkness, we recall that even the arrangement of galaxies forms a vast, cosmic web of filaments and voids, stretching across hundreds of millions of light-years. The large-scale structure of the universe is like a spiderweb lace of galaxy clusters surrounding immense empty bubbles. Against that backdrop, an odd alignment in the cosmic microwave background, like the axis of evil, is especially intriguing. It suggests that on the grandest scales, the universe might have subtle symmetries or hidden structures that we haven't fully grasped. We find this deeply intriguing. The idea that the entire sky's baby picture of the universe might contain hidden messages or oddities. Having pondered these grand, subtle oddities, we turn our thoughts to a different kind of cosmic mystery, one that has captivated humanity for generations. Are we alone in the universe? Amid all these stars and galaxies, might there be other intelligences, other civilizations reaching out across the void? Our journey has so far been filled with natural phenomena, but one anomaly that continues to tantalize is the absence, or faint hints, of extraterrestrial communications. Now, we let our minds reach out into that silence, listening for any whisper from the stars. We tune our imaginary antennas to the sky and listen. What we hear is mostly a deep and static hush, the natural background noise of stars and galaxies. For decades, scientists have been conducting a real-life cosmic eavesdropping known as SETI, the search for extraterrestrial intelligence. Giant radio dishes have scanned the heavens for any hint of an artificial signal amidst the cosmic static, a beacon, a melody, a coded message from another civilization. It is a bit like standing in a vast empty cathedral and hoping to hear a distant whisper. So far, no indisputable communication has been heard. The silence has led to philosophical musings, the so-called Fermi paradox. If the galaxy is teeming with worlds, where is everyone? Yet, there have been a few tantalizing enigmas. The most famous is the WOW signal. On an August night in 1977, a radio telescope in Ohio recorded a strong, narrow-band radio signal from the direction of Sagittarius. It was unlike the normal background noise, and exactly the kind of signal one might expect from an interstellar transmitter. A surprised astronomer scribbled "Wow" next to the data, giving the event its name. The signal lasted 72 seconds and never reappeared. Numerous attempts to find it again or identify its source failed. To this day, we cannot say for sure what it was. It didn't contain any obvious message. It was just a rise in intensity at a specific frequency, around 1420 MHz, notably the natural emission line of hydrogen. Some suspect it might have been an unusual natural emission, or a reflection of an Earth signal, off space debris. Others indulge in the thought that perhaps, just once, we briefly eavesdropped on an alien beacon as it swept past us. The mystery remains unresolved, hovering between the prosaic and the profound. Other curiosities have popped up and faded. For instance, in 2017, astronomers discovered an object passing through our solar system on a hyperbolic trajectory, clearly visiting from interstellar space. Named Oumuamua, it had a strange elongated shape and showed a slight non-gravitational acceleration as it departed the Sun, leading to speculations that it might be a light sail or probe sent by an alien civilization. Further study indicated it was likely a natural fragment of a comet or something unusual, but not powered by engines. Nonetheless, Oumuamua was a reminder that mysterious visitors can arrive unexpectedly, and we should keep our minds open even as we seek mundane explanations. Astronomers occasionally detect odd radio bursts, like the recently discovered fast radio bursts, FRBs, that are now attributed to exotic neutron stars, which initially spurred speculation about extraterrestrial communications. Each time, nature has thus far provided a natural explanation. But the search continues, more refined than ever. Projects now are scanning millions of star systems across multiple channels, and even looking for optical signals, like laser flashes, or other technosignatures, like unusual chemical pollutants in exoplanet atmospheres that might indicate technology. It's a vast cosmic hide-and-seek, and we've only just started looking under the nearest lamps. When we consider that our own radio broadcasts have been leaking into space for just about a century, forming a barely perceptible bubble 100 light-years in radius, and our galaxy is 100,000 light-years across, it's no wonder direct contact is elusive. Civilizations could be sparse and far apart in time or space. Perhaps many exist, but are content to listen, not transmit, just as we mostly are. So what appears as silence might be a mutual waiting, like two people in a dark forest, each hesitant to call out. Sometimes, rather than listening for signals, scientists have looked for technological footprints in the data of astronomy. One intriguing idea is to search for alien megastructures, massive constructions built by advanced beings, which might be observable by their effects on starlight. In the 1960s, physicist Freeman Dyson proposed that sufficiently advanced civilizations might build enormous swarms of solar panels around their star to capture most of its energy, often referred to as a Dyson sphere. Not necessarily a solid shell, but perhaps a swarm of satellites. Such a feat would drastically alter the star's observable properties. For instance, it might dim the star's light in peculiar ways, or radiate lots of infrared from the waste heat. For decades, this was mostly theoretical musing. But then, in 2015, astronomers noticed something odd about a star catalogued as KIC 8462852, now nicknamed Tabby's star after Tabitha Boyajian, the scientist who led the study. This star, about 1,500 light-years away, was observed to dip in brightness irregularly by up to 20% and for unusual lengths of time. These dips did not match the pattern of a planet transiting the star. They were too deep and not periodic. Naturally, a range of explanations was proposed, perhaps a swarm of comets passing in front of the star, or an irregular cloud of dust orbiting it. But one speculative idea captured public imagination. Could it be a partially constructed Dyson megastructure, like giant panels occasionally blocking the star's light? In other words, an alien megastructure. For a while, Tabby's star sparked wide discussion. Follow-up observations and analyses have since provided evidence that the dimming is likely caused by dust. Different colors of the star's light are dimmed by different amounts, which points to fine dust grains rather than solid megastructures. So the alien hypothesis has lost favor, as it usually does when more data arrives. But the very fact that we even considered it seriously is telling. It shows both our keen desire to find others and our method of exhausting natural explanations while keeping an open mind. Tabby's star was a natural mystery first and foremost, but it reminded us that if alien engineering is ever to be found, it might first appear as a strange astrophysical anomaly. And there are other ideas. Perhaps advanced civilizations might leave detectable signatures like intense beams of neutrinos, or alterations of stellar spectra, or even moving stars or asteroids around stellar engines. None of these are observed yet, but the universe is vast, and our observation time has been short. So we continue to listen and watch. Late at night, radio telescopes swivel silently under the stars, like giant ears poised for a hint of a cosmic sonata. Now and then, an observatory might pick up an intriguing pulse or pattern, sending scientists into a flurry until it's identified. Famously, a series of pulses once confounded researchers until they realized it was the microwave oven in the break room being opened mid-use. The silence thus far isn't discouragement, but rather part of the wonder. It emphasizes the rarity and preciousness of life, or at least of intelligent life that communicates in ways we can detect. Perhaps we truly are rare, a fleeting spark in a dark cosmos. Or perhaps the galaxy is full of life that is content in its own local spheres. Perhaps many civilizations simply pass through a phase of emitting signals and then retreat into quietude. We don't know. But in the absence of answers, we have the questions and the hope. In this gentle quiet, one can also find a kind of peace. If indeed the stars are silent, we still have their beauty and the gift of solitude in which to contemplate creation. And if someday a new pinpoint of radio light appears, carrying a deliberate greeting, or a distant star begins to pulse in prime numbers, that too would be a profound, stirring moment. Until then, the quietude of the night sky remains a canvas for our dreams and curiosity. We raise our gaze now from individual stars back to the grand cosmic canvas and turn to thoughts even more expansive. The ultimate fate of the universe itself and the deepest questions of time and existence. Our journey would be incomplete if we did not, at least in passing, ponder how all of this might eventually end, and if an end is even the end. The universe had a beginning, as far as we know, in the Big Bang roughly 13.8 billion years ago. And naturally we wonder, will it have an end? And if so, what will that end be like? Gazing up at the stars, it's almost impossible to imagine them all gone. The galaxies dark, the cosmos transformed into something truly alien compared to its current brilliance. Yet modern cosmology suggests a variety of scenarios for the far future, some eerily quiet and others catastrophically violent. As we drift now into conjecture, the scale of time we consider is immense. Trillions of years, googles of years, 10, 100, and beyond. It's a realm where even the word forever starts to take on nuanced meanings. One widely accepted fate, given our observations of an ever-expanding universe, is the so-called heat death, or big freeze. In this scenario, the expansion of space continues indefinitely, and over incomprehensible spans of time, the cosmos approaches a state of maximum entropy, disorder. Stars will be born for a while yet. Simulations suggest new stars can continue to form for up to 100 trillion, 10, 14 years. But eventually, the gas needed for star formation will be exhausted or locked away in remnants. The existing stars, one by one, will exhaust their fuel. The massive ones will go supernova or collapse into black holes. The lighter ones will end as white dwarfs and slowly cool. Planets, if still orbiting, may freeze or wander off. Bit by bit, lights wink out. In perhaps 10 to 14 years, the last main sequence star will shine its last. The universe then becomes a graveyard of stellar remnants. White dwarfs, neutron stars, black holes, and cold planets. With no new energy sources, these too will fade. White dwarfs will radiate their remaining heat for quadrillions of years, turning into black dwarfs, hypothetical, cold, dark, stellar corpses, though none exist yet, as the universe isn't old enough. Fast forward further. In about 1019 to 1020 years, galaxies themselves will no longer hold together. Gravitational encounters will gradually throw stars out of galaxies or cause them to spiral into central black holes. The night sky, for any hypothetical far future observer, would grow emptier as the stars disperse into the expanding void. If protons are unstable, some theories suggest protons might decay after 10 to 34 years or more, then eventually, even matter, as we know it, will disintegrate into radiation and subatomic particles. Black holes, seemingly eternal, actually have a finite life too, according to Stephen Hawking's theory. They slowly evaporate by emitting Hawking radiation. For a stellar mass black hole, this takes 10^67 to 10^100 years. For the supermassive black holes at galactic centers, the evaporation time is even more colossal, on the order of 10^100 years or beyond. But given enough trillions upon trillions of years, even those giants would evaporate, fading with a whisper of photons into the darkness. What remains then? A thin, cold soup of particles and very low energy radiation, spread so diffusely that, on average, almost nothing happens anywhere. The temperature of the universe would asymptotically approach absolute zero. Time still passes, but practically speaking, the universe becomes static. No gradients, no free energy to perform work or sustain complexity. This is the heat death. It is not a dramatic bang or collapse. It's the slow fading of light and structure, ending in an eternal night. In that final darkness, if consciousness still somehow exists, time would lose meaning because nothing changes. It's a haunting thought, an infinite future of silence and cold. But remember, this outcome is trillions of times farther in the future than the current age of the universe. It lies so far beyond our human epoch that it almost becomes an abstract contemplation, like pondering infinity. There are other scenarios. Another possibility, though current data suggests it's less likely, is a cataclysmic disruption known as the Big Rip. This would occur if the mysterious dark energy driving the universe's accelerated expansion is not constant, but actually grows stronger over time, particularly if its equation of state has a value W(1), sometimes called phantom energy. In a Big Rip scenario, the repulsive force of expansion increases without bound, eventually overcoming all other forces. Eons from now, perhaps 22 billion years in the future in one model, the expansion would reach smaller and smaller scales. First, galaxy clusters would be torn apart, then individual galaxies, then star systems. In the last few minutes, again, far in the future, even stars and planets would be ripped to shreds. In the final seconds, atoms themselves would be sundered, and finally, even atomic nuclei and fundamental particles might be ripped apart as the fabric of space stretches violently. The universe would end as a very strange state, a highly accelerated expansion with everything blown apart into isolated particles and radiation. Effectively, a featureless void. Unlike heat death, which is a gentle petering out, the Big Rip is a more dramatic, if quick, death by dismemberment of all structures. It must be noted that this scenario hinges on a form of dark energy that current evidence doesn't strongly support. Our observations so far are consistent with a constant dark energy, cosmological constant, that leads to heat death, not a runaway. But the uncertainty in the nature of dark energy leaves a sliver of possibility for this more violent end. There's also the intriguing, if somewhat unsettling, prospect of a vacuum decay event. Our current physics models suggest that what we call the vacuum, empty space, might not actually be the ultimate lowest energy state of nothingness. It could be a false vacuum, a somewhat stable state that isn't absolutely stable? If so, there is a possibility that through a quantum tunneling event, the vacuum could decay to a true vacuum, a state of even lower energy. If that were to happen, a bubble of this true vacuum would appear at some point in space and then expand outward at nearly the speed of light, obliterating anything it encounters, because the laws of physics inside that bubble could be different. Fundamental constants might change, particles we know might not be stable. It's a doomsday scenario that would be instantaneous and without warning. One moment the vacuum is as we know it. The next moment, a bubble of alien vacuum is rushing out. However, before we lose sleep, most calculations indicate that if our vacuum is metastable, its lifetime before such an event occurs is extraordinarily long, something like 10⁻⁷ or 10⁻⁻1000 years. In fact, a recent calculation put it at about 10⁻⁷90 years. These numbers are beyond astronomical. They dwarf even the timescales of heat death. So while vacuum decay is theoretically possible, it's not something we expect to happen any time in the foreseeable or nearly unforeseeable future. The universe likely has plenty of life left in it. All these scenarios assume no intervention and a solitary universe. But some have imagined ways in which intelligent life, if it endures far into the future, might mitigate or sidestep these fates. Concepts like creating pocket universes or harvesting energy from black hole rotations to prolong warmth, or even migrating into a hypothetical multiverse if such a thing is possible. Those ideas cross into the realm of science fiction based on slim extensions of science. Yet, when considering eternity, it's hard to resist a touch of creative speculation. There is also the thought that perhaps an ending is not truly the end. Some cosmological models suggest cycles. A universe could collapse, big crunch, and then rebound into a new big bang, big bounce. Or a new universe might be born from the death of a previous one. Currently, our universe's expansion seems destined not to collapse, but to continue, so a big crunch is not favoured. Yet, on the grandest canvas of multiverse theory, maybe our universe is just one bubble among many, and new bubbles big bang into existence now and then. Sir Roger Penrose has a theory called conformal cyclic cosmology, where the remote future of an expanding diluted universe can be mathematically transformed into the extremely hot, dense conditions of a new Big Bang, essentially connecting the end of one eon to the beginning of another. If something like that were true, then the heat death isn't an eternal prison, but rather the chrysalis for a new creation. On a more philosophical note, there's eternal recurrence. Not necessarily in the strict physical sense, but as a concept that if time and space are infinite, perhaps every configuration of matter, including you and me and this entire journey, might happen again and again, infinitely often, in an infinite universe or multiverse, with infinite time. The idea of Poincaré recurrence suggests that systems could return arbitrarily close to their initial state, given enough time. Some thinkers and science fiction writers have mused that perhaps after an inconceivably long period of darkness in a heat-dead universe, random quantum fluctuations could trigger a new localized Big Bang or coalesce particles into something like a new Big Bang seed. Or, in an infinite multiverse, maybe events identical to our universe are playing out elsewhere or will play out again. These ideas blur the line between physics and philosophy and currently reside more in the imaginative realm than in testable theory. But it's a poetic notion. The cosmos might regenerate, like a phoenix, or that time might be a wheel rather than a line. As we entertain these cosmic endgames and potential renewals, a gentle humility settles in. The fate of the universe is a story that will unfold on scales of time vastly beyond our lives, our planet, even beyond the lifespan of galaxies. It makes our own era, this age of shining stars and rich galaxies, feel like a special, perhaps fleeting time in the cosmic calendar. We happen to exist when the universe is vibrant and young, full of light and curiosity. In tens of billions of years, the night sky will look very different. But right now, overhead, we still have the Milky Way's starry band, the whirls of galaxies reachable by telescopes, the glow of nebula and the steady rhythms of pulsars, all there for us to witness and ponder. Our journey has taken us from the crackling remnants of dead stars to the nurseries of new ones, from mysterious signals and structures to the twilight of existence itself. It has been a voyage not just through space, but through time and possibility. In the end, perhaps the greatest anomaly of all is that we are here, conscious beings made of stardust, able to reflect on the universe's mysteries. We hold that thought as we gently begin to conclude our expedition. The stars above and the particles and waves all around continue their dance as they have for eons. The universe in this moment is vast and dark, yet dappled with light and wonder. There are questions unanswered, and that is a beautiful thing, for it means there is always more to learn, more to dream about. If you lie under the open sky on a clear night, far from city lights, you can see the soft band of the Milky Way arching overhead. Thousands of stars glimmer, a fraction of all those that are really there. In the stillness, you might feel the tug of mystery, the same curiosity that propelled us on this imaginary voyage. A gentle breeze on earth might rustle the grass, but your mind drifts easily back to the stars. Perhaps a shooting star, a tiny meteor, streaks briefly, reminding you that even as you gaze up, small pieces of the cosmos are coming to visit. In moments like this, the boundary between you and the universe feels beautifully thin. Now, as our exploration winds down, we let the enormity of it all dissolve into a calm appreciation. The cosmic ocean is still there, gently sparkling with distant galaxies, like islands in a great dark sea. We have dipped our senses into that ocean and felt its depth. In our mind's eye, we float one last time among the stars, feeling small, but connected to something so grand. A serene darkness enfolds us, not as something frightening, but as a warm cradle for all existence. The heartbeat of a pulsar, the glow of a nebula, the silent song of a galaxy. All these echo softly in our memory. The darkness between the stars is deep and eternal, a gentle cradle for the quiet aftermath of cosmic events. In this silent expanse, time itself seems to hold its breath. We have wandered through epochs of starlight and shadow, witnessing the birth of suns and the death of worlds. We have drifted by cosmic abysses where even light succumbs to darkness, and contemplated the distant future where the last stars wink out. Now, in the hush beyond all that is known, our journey carries us further still, into realms of speculation and wonder that stretch the imagination. Far beyond the last glowing ember of our universe, beyond the horizon of what we can see or touch, there may lie other realities. The mind drifts to the possibility that our cosmos is not alone. Perhaps, scattered in an unfathomable void, there are countless other universes, each as vast and mysterious as our own. In this dreamlike vision, the universe we know is but one bubble afloat in a limitless cosmic sea. Around us, in dimensions beyond our comprehension, other bubbles might shimmer, births of other big bangs, expanding realms of space and time with their own galaxies and stars. Floating in this thought, one imagines an endless foaming ocean of universes. Each bubble universe drifts quietly, isolated yet part of a greater whole, much as galaxies are isolated islands of stars in our night sky. Some bubbles might gently collide in the far distance, merging or giving birth to something new. Others remain solitary, forever out of reach of one another, each containing wonders and laws, perhaps entirely different from our own. The boundaries of these universes are soft and diffuse in this reverie, as if separated by the thinnest of veils. Our own universe had a beginning, a moment of furious creation when time and space blossomed from seemingly nothing. Could it be that this birth was one of countless births happening eternally? Some theories whisper of eternal inflation, a process where the cosmos expands ceaselessly, spawning new universes as it grows. In that picture, our universe was born from a mother universe, like a new bubble inflating off the side of an ever-growing foam. Another idea envisions our universe as a membrane floating in a higher dimensional space, one of many. If two such cosmic brains were to collide, their impact could trigger a big bang and create a new universe. In either scenario, each new universe emerges with its own initial spark, its own tapestry of space-time, then drifts off, expanding and evolving on its own. It is a strange and beautiful thought that the night sky we gaze into is not the only sky, that beyond that ultimate horizon of billions of light years, beyond where even our telescopes cannot see, there may be other skies with other stars, and perhaps other beings gazing up at their own sky. Under an alien set of constellations, in another universe, maybe a conscious mind wanders in its own way, unaware of our existence, just as we cannot be sure of theirs. And perhaps, in some subtle fashion, all these separate worlds are part of a single cosmic tapestry, connected through the mysterious process that gave birth to them all. As we drift further into this speculation, the boundaries between science and poetry blur. We envision not just space, but a grander expanse in which many spaces float like lanterns in the dark. Each universe lantern glows softly with the light of its galaxies, enduring for eons, then perhaps fading. But even as one flickers out, new lights may appear elsewhere in the infinite night. One can almost feel the quiet of this multiversal night, a deeper silence than any one universe alone could hold, a serene expanse where creation and destruction play out like notes in a cosmic melody. In one universe, stars are being born at this very moment, brilliant nurseries of light blossoming in nebulae. In another universe, perhaps stars never formed at all, just endless dark or some completely different kind of structure that we cannot imagine. And in yet another, maybe the laws of physics took a slightly different turn. Perhaps gravity is stronger there, pulling matter into dense spheres more swiftly. Perhaps in another, there are additional dimensions of space, curling in ways we would find bizarre and beautiful. There is also the notion that multiple realities might exist not only as separate bubble universes far away, but as parallel versions of our own universe, branching off at every moment. According to this idea, often called the many worlds interpretation, whenever a choice is made or a chance event occurs, the universe could split into different paths. In one path, a star might explode in a supernova. In another, it might remain intact for eons. In one branch of reality, a comet missed an ancient Earth, while in another branch it struck and altered the course of life's history. These parallel worlds would be like shadows of our own, each as real as ours, but unreachable, forever separated by the branching of possibility. If this is true, then reality is a constantly diverging tree of universes, each branch carrying on its own story. We would only ever experience our particular branch, unaware of the countless others where events unfolded differently. This vision of the multiverse is more intimate and continuous, woven into the fabric of quantum happenings all around us. Yet it remains as ethereal as any other idea of multiple worlds, something we cannot touch, but can only imagine with a sense of quiet awe. All these possibilities swirl gently in our mind's eye as we contemplate the multiverse. It is an idea, both comforting and disorienting. Comforting in that existence might be boundless, always renewing itself with new worlds, meaning that creation never truly ends. Disorienting, because it suggests that what we thought was everything is only a tiny part of a far vaster reality. Yet here, in the quiet cosmic night, we allow these thoughts to come and go like passing clouds, without need for certainty. We simply observe them as part of our slow journey. Through this perspective, even the ultimate fate of our own universe, the long dark ages that we once envisioned as the end, may be just one chapter in an endless story. If our universe grows cold and empty, perhaps elsewhere another one is blooming warm and bright. The cosmos may have gardens in many places, each coming to life in its season. Our hearts feel a gentle reassurance in this. The end of one thing could be the beginning of another. The void is not truly empty if beyond it lie other worlds. And if these other universes exist, they raise enchanting questions. Are they completely separate, forever unreachable? Or is there some subtle connection, like a hidden thread that links them? Could there be rare moments where two universes brush against each other, like gossamer veils touching in the dark, allowing a whisper of one reality to pass into another? Perhaps such an event could be behind some of the unexplained anomalies we've encountered, a strange signal, a burst of energy with no clear source, a mystery particle that vanishes as soon as it's observed. These could be nothing, or they could be faint echoes from another realm, gentle reminders that reality is more layered than we thought. In this meditative exploration, nothing is certain except the wonder of not knowing. We remain adrift in possibilities, letting each image form softly in the mind and then dissipate. The idea of a multiverse is not something we can prove or see directly, at least not yet. It lives at the edges of science and imagination. But here, under the tranquil blanket of cosmic night, we allow ourselves to wander those edges, finding them as mysterious and beautiful as the known universe itself. The multiverse, if it exists, may be like an endless forest of worlds. One might imagine it as a forest at night. Countless fireflies flicker in the darkness. Each tiny light could be a universe. Some glow brightly for a time, then fade as their energy dims. Others might pulse rhythmically, their internal events perhaps cycling through expansions and contractions. We stand at the edge of this metaphorical forest, watching the dance of creation across a boundless expanse of possibility. There is no rush here. The fireflies move slowly, and so do our thoughts. And as we watch this grand display in our mind's eye, a thought arises gently. What lies beyond even this? If all these myriad universes exist, what space holds them? Is there an even larger expanse, a metacosmos that cradles all of the bubbles and all of the fireflies? If so, is it calm and static? Or does it too have its own rhythms and tides? The questions drift by like distant galaxies, each one far away and faint, not demanding answers, but simply adding to the depth of the mystery. We realize that the more deeply we peer into existence, the more endless it becomes, like traveling down a never-ending road that forever opens new horizons. In this way, our journey into the multiverse becomes a journey into awe itself. We have stepped beyond the edge of the map of our understanding, into the infinite unknown. And here, rather than fear, we find tranquility. The unknown is vast but gentle. It does not press upon us. It simply is. We are a small, quiet witness to its immensity. We feel ourselves just a tiny part of something so large we cannot truly grasp it. Yet that thought is strangely soothing. We do not need to grasp it. We can simply be here, observing the glimmer of countless possible worlds in the dark, and feeling the deep peace that such perspective brings. Slowly, the vision of myriad universes begins to dissolve into a soft darkness. We let the concept of the multiverse recede to the background of our mind, like a distant star fading from view as clouds drift over. It remains somewhere out there, in the depths, twinkling quietly. But now our attention returns gently to the present universe, our universe, and to another fundamental aspect of reality that we often take for granted: time. Time, that ever-present current in which all events unfold, now becomes our focus. In our everyday experience, time flows like a gentle river, carrying us along from moment to moment. We mark its passage with heartbeats and breaths, with the turning of planets and the burning of stars. Yet, as simple as it seems, time holds deep secrets and anomalies, especially out here in the cosmic wilderness. In the vast stillness of space, time can twist and warp in ways that defy our ordinary understanding. Near a massive star or the maw of a black hole, the flow of time itself slows down. If we could watch a clock drift close to a black hole's edge, we would see its hands moving ever more sluggishly. A second might stretch to feel like an hour from our distant vantage point. To the clock itself, were it conscious, nothing would seem amiss. It would tick normally in its own experience. But to us far away, it would appear nearly frozen. Such is the strange flexibility of time. What is a heartbeat for one observer might be a millennium for another, depending on how gravity and motion weave their influence. In our imagination, we picture an astronaut venturing near a massive black hole, then returning to her home planet. She finds that while only a few years passed for her, many decades slipped by for those she left behind. Children she knew might have grown old in her absence. This isn't science fiction, but a consequence of nature's laws, a gentle bending of time itself by gravity and speed. How marvelous and disconcerting that time, which we assume is universal and constant, is in fact personal and malleable. And it grows stranger still. The tapestry of space and time is woven together, what we call space-time, and it can fold in unexpected ways. There are solutions in physics, like rare gems hidden in equations, suggesting that time might form a loop. Imagine traveling through space and, because space and time are linked, finding oneself arriving not just in some far-off place, but some far-off time, perhaps even to the past, coming full circle to moments that have already been. These hypothetical loops are called closed time-like curves, paths through the cosmos that bend back on themselves in time. If such a path could be found or created, one might, in theory, walk along it and step into yesterday or years gone by. It is a notion that challenges our sense of cause and effect, a paradox at the edge of understanding. We do not know if nature allows such loops in reality. Perhaps they exist only in mathematics and imagination, or perhaps out in the wild cosmos, under exotic conditions like a rapidly spinning black hole, or the peculiar gravity around hypothetical cosmic strings. Time might curl in on itself briefly, like an eddy in a great river. If one could drift into such an eddy, what would it feel like? Would a traveller relive a moment over and over, caught in a cosmic déjà vu? Or could they break free and find a new timeline branching from that twist? The questions themselves swirl in their own loop, with no clear answers. In the spirit of our meditative journey, we need not solve these riddles, we simply float among them, observing their shapes. Even without fantastical loops, time is full of riddles. We experience it as a one-way street. Memories lie behind us, the future unknown ahead. But the fundamental laws that govern particles and planets don't themselves insist on an arrow moving forward. They are surprisingly symmetrical, as if time could run backward and the equations would still make sense. Why then do we sense an irreversible flow? Why do stars age and not unage? Why do we grow older and not younger? The answer seems tied to the idea of entropy, the tendency of things to move from order toward disorder. A star's bright heat disperses into space and cannot be gathered back. Once eggs are scrambled, they cannot unscramble. Once a drop of ink spreads in water, it won't spontaneously recollect into the drop. The universe started in a state of low entropy, high order, and ever since, entropy has been increasing, giving a direction to time that we all feel. This is the arrow of time, from order to disorder, from past to future. Yet, at the smallest scales of physics, the distinction between past and future blurs. One could watch a microscopic interaction in reverse, and it would look plausible. Only when many particles come together, as in a puff of smoke dispersing, or a star burning its fuel, does a clear direction emerge. How fascinating that the flow of time we take for granted might not be a fundamental truth, but rather a consequence of how our universe began and how complexity grows. In the grand, quiet cosmos, one can almost sense time's arrow stretching across eons, from the smooth, hot light of the Big Bang to the structured galaxies of the present, and onward into the diffuse haze of the far future. It's like an invisible wind that has been blowing since the dawn of time, guiding the universe from its simple infancy towards its complex, aged future. Some thinkers have taken these ideas further, proposing that time might not be fundamental at all. In the deepest laws of reality, time could be absent, a bit like a melody that emerges only when the full orchestra of the universe plays together. Perhaps every moment, past, present, future, already exists in a grand, timeless map, and what we call the flow of time is just our consciousness, moving from point to point. reading the story line by line. Under this view, the universe could be like a novel already written from beginning to end, sitting timelessly on a shelf. We living beings are simply leafing through it at a steady pace, experiencing each page as the present. The characters in a book have no sense of the whole story, only the current page. Just so, we never see the future pages, only the now. In this timeless perspective, one can imagine rising above the plane of time entirely, seeing all history at once, like gazing at a vast mural instead of a single frame of a movie. Of course, this is beyond human capability. We are bound to time's flow. But just thinking of it brings a strange peace. If all moments in time exist at once, then nothing is ever truly lost. It simply has its place in the tapestry. The first light of dawn on the first stars, the final ember at the end of time, both exist in the grand design, each eternal in its own coordinates, even if we experience them sequentially as fleeting instants. We only ever witness one moment at a time, as if walking a path through an endless landscape. Even though we conceive of these lofty ideas, we still feel the reality of each moment passing. Out here in the quiet dark, 1 second follows another with metronomic calm. In the far future, if the universe continues expanding and aging, time might stretch further and further between meaningful events. Picture a moment, trillions of years from now, when galaxies have drifted so far apart that an observer in one might see only darkness, no other stars beyond its own cluster. In such isolation, time could feel nearly frozen, with hardly any change from one eon to the next. In a universe that has gone quiet and cold, would time lose its meaning? Perhaps in that final stillness, where nothing happens and nothing changes, time itself effectively stands still. An eternity of night, where the difference between one moment and another blurs into nothingness. Alternatively, if the cosmos has cycles or rebirths, time could be circular on the grandest scale. Some have mused that the universe might end in a collapse or big crunch, only to explode again in a new big bang, a cosmic phoenix rising from its own ashes. If that were true, time as we know it might be part of a loop that resets, making the ultimate timeline a circle without beginning or end. But our current observations suggest an ever-accelerating expansion toward a quiet end, more like a one-way road into darkness. Reality may be neither a simple circle nor a simple line, but something more complex and subtle. Here, in the quiet of our minds, we do not need to decide the fate of time. We simply feel its mystery. We recall how elastic it can be, how a joyful afternoon can race by in a blink, or how a lonely night can drag on endlessly. Our perception is a poor clock. In stillness, with closed eyes, sometimes an hour can feel like a moment, as thoughts drift, untethered by the outside world. Other times, a few minutes of waiting in anxiety can feel like an eternity. In a sense, each of us is a time traveler moving at the speed of life, experiencing a personal timeline shaped by our path through space and gravity and emotion. The cosmos provides its own commentary on time through phenomena like pulsars, the remnants of supernovae, that blink with astonishing regularity, like the ticking of a galactic clock. Some pulsars spin hundreds of times a second, so steadily that their beats rival atomic clocks in precision. They remind us that even amidst the wild, natural universe, there are timekeepers. Yet elsewhere, near a black hole, time's pace can nearly halt relative to a distant observer. The contrast is profound. Time has not one rhythm, but many, all valid in their own frame. No single clock rules the universe. Instead, each object carries its own little clock, and they can disagree and still all be right. Gently, we consider that perhaps time is ultimately a human way of making sense of change, a concept we derive from memory and expectation. The universe simply is. Events happen, configurations change. But the flow we feel may be a kind of illusion crafted by our minds to link it all together. Some physicists suggest that what we perceive as the passage of time might emerge from something deeper, like quantum entanglement or the growth of complexity in the universe. To them, time might be a secondary concept, a convenient story we tell ourselves as particles dance to more fundamental rules that themselves may be timeless. These are profound ideas that border on philosophy, yet they spring from attempts to understand reality at the deepest level. The longer we ponder time, the more dreamlike it becomes. Imagine for a moment that time is like a vast, still ocean, and we are little boats moving across it. We create ripples as we glide, marking our passage. But the ocean itself is calm, not flowing anywhere, just existing. Or picture time as a grand stage on which the universe plays out its scenes. When the play is done, the stage remains for the next story, unchanged by the drama. If the stage itself were alive, it would not notice the fleeting acts that come and go. So too might a timeless perspective see our whole history as a single, exquisite pattern, already complete. These reflections on time begin to settle now, like golden sand, sinking in a tranquil pond after being stirred. We feel a sense of equilibrium, accepting time's mysteries without needing to solve them. In the darkness of space, each moment flows into the next like a gentle tide. Clocks may tick, galaxies may turn, but here in our quiet contemplation, time is simply part of the background hum of the cosmos, a patient, persistent lullaby counting out the ages. As this realization takes root, our attention starts to move beyond time. We have explored the vast multitude of possible universes and toyed with the enigma of time's nature. Now, a new question arises in our cosmic reverie. What is the fundamental nature of this reality we inhabit? Could it be that everything we see, the stars, the galaxies, the very fabric of space-time, is not as it appears? A subtle notion glimmers. Perhaps the universe is less like a machine and more like a thought, an idea, or even a kind of elaborate illusion. In the quiet depths of contemplation, we turn toward the notion of the universe as a grand design or simulation, an information dream that a deeper reality might be dreaming. What if all that we see around us, the shining stars, the swirls of galaxies, the fields of cosmic dust, are, at their core, an illusion? Not an illusion in the sense that they aren't there, but in the sense that they might be a grand simulation or a cosmic dream. In the stillness of our mind, we entertain the idea that the universe could be like a great thought in the mind of some unknowable entity, or like a program running on a cosmic computer beyond our reach. It is a notion both strange and intriguing, that reality might be made not of solid matter and energy at the deepest level, but of bits of information, like the binary code in the heart of a computer's software. Under the veil of night, with stars as our only witnesses, we muse softly about this possibility. We recall how mathematical the universe is. Galaxies follow precise orbits, planets dance in ellipses, particles obey statistical rules and equations. It's as if a kind of code is built into nature itself. Equations are the language through which we describe the cosmos, and they work with astonishing accuracy, predicting phenomena across billions of light years and billions of years of time. Could it be that these equations are describing something akin to software underlying reality? Perhaps the reason the universe is comprehensible through mathematics is because, in a sense, the universe is mathematics, geometry and numbers, given the breadth of physical existence. If the universe is a program, one might imagine the Big Bang as the moment of booting up, an instant when the lights flickered on and the rules were set in motion. Since then, the cosmic program has been running for eons, evolving complexity from simple beginnings. Galaxies have formed like vast, self-organizing patterns. Stars ignited like luminous nodes, processing energy. And life emerged like self-replicating subroutines, exploring the data of experience. We, as conscious beings, could be part of this program. Our thoughts, the result of electrical impulses in brains, which themselves could be seen as computations. In a simulated universe, everything we do might be akin to an algorithm running, and every atom might be storing bits of information about its state. Such an idea can make one feel small, like a character in a story might feel upon suspecting they are written into a tale. But in truth, whether the universe is a simulation or not changes little about our experience. We still feel love and wonder. We still marvel at the stars and ponder the unknown. If this is a simulation, it is an exquisitely rich and beautiful one, with detail and depth far beyond anything we humans know how to create. And importantly, from within it, it is as real as anything. A character in a perfectly crafted simulation would live and love and strive with the same intensity as one in a base reality. The sunsets would still paint the sky in rose and gold, stirring the heart. The bonds between living beings would still feel warm and meaningful. Nothing in our human experience is diminished by this perspective. It merely frames it in a new way. We gently turn the idea over in our mind. If there is a code underlying everything, are there hints of it that we can detect? Some wonder about the remarkable coincidences in physics, how the constants of nature, the strength of gravity, the charge of the electron, and so on, seem just right for stars and life to exist. In the simulation view, one could imagine these as carefully chosen settings in a cosmic program. Others muse about quantum mechanics, particles that seem to pop in and out of existence, or only decide on a state when observed, almost like a graphical engine that only renders what the player is looking at. Could it be that reality has a kind of lazy loading, revealing details only upon interaction, similar to how a video game loads only the part of the world the player explores? These analogies are speculative, whimsical even, but they tantalize the mind. Yet, If our universe is a simulation, it raises profound questions. Who or what created it? Perhaps an advanced civilization in another universe, or our own far future, running ancestor simulations of their past. Or maybe the simulator is not something we can comprehend at all, not a being or a machine as we know it, but some fundamental layer of reality playing out possibilities. Is the simulator benevolent, curious, indifferent? Is there a purpose to our simulation? Or is it an art project? Or just one simulation among countless others, like a naturally occurring pattern? The possibilities branch out into the unknown. It's easy to get lost in the maze of maybes, but here in our tranquil reflection, we do not let it become a source of anxiety, only gentle wonder. We accept that if we are in a grand experiment or a cosmic dream, then that is simply another facet of existence to marvel at. It changes nothing about the kindness we should show or the curiosity we should feel. We simply add it to the list of mysteries and carry on experiencing the beauty around us. Another curiosity arises. If this is a simulation, could there be ways to tell from the inside? Might there be glitches in the matrix of reality, subtle inconsistencies hinting at an underlying code? People have pondered whether tiny anomalies in astronomical observations or physics experiments could be the fingerprints of coding. Perhaps the very small irregularities in the cosmic microwave background, or some unexpected result in a particle accelerator, is a sign that our reality has an edge or a pixelation to it. Others playfully imagine déjà vu, or the sensation of coincidences, as potential glitches, like the program momentarily repeating or intersecting with itself. These ideas are mostly fanciful. Our universe, simulated or not, runs so smoothly and consistently that it's hard to imagine catching it in an error. If a higher reality set ours in motion, they did so with masterful finesse. Consider also, if our universe is simulated, does that mean everything is predetermined by the code? Or could we have genuine free will inside it? In a simple computer program, characters do only what they are programmed to do. But maybe this simulation is different, more open-ended, with emergent properties. Perhaps the code provides the rules and initial conditions, and what unfolds is not pre-scripted, but evolves freely. In that case, we, with our thoughts and choices, would be part of the unfolding story, not mere puppets on strings. We would be agents exploring the space of possibilities, just as we feel we are. It's comforting to think that even if reality is a kind of computation, it might still allow for creativity, surprise, and genuine freedom within it. Now think of the possibility of nested worlds. If one advanced universe can simulate another, perhaps this can happen again and again. We could be a simulation within a simulation, layers down, like a dream within a dream. And perhaps we ourselves will one day create simulated universes with conscious beings inside, not realizing that we too are in one. The idea cascades like reflections between facing mirrors, seemingly infinite. Yet, in the stillness of night, this infinity of reflections is not frightening. It's oddly serene. It implies a continuity of creation, that realities can be born from other realities, a chain that might extend without end. It makes the question of what is truly real feel more fluid. In a sense, if there is always a deeper layer, reality is relative. And if it's relative, maybe the distinction between simulation and reality loses its meaning. Perhaps reality is simply the level we are on, and it is genuine to us. After wandering through these far-reaching thoughts, we come to a simple conclusion. Whether or not our universe is a simulation, here we are, part of it, inseparable from its fabric. We feel the cool night air of our planet, or the memory of it, if we only imagine ourselves outdoors right now. We see the dim light of distant stars, and we know that we exist right now with the capacity to wonder. Simulated or not, this moment is what it is, precious and real to us. Our responsibility and our joy is to experience it fully, to be kind within it, to seek understanding, and to appreciate the beauty it offers.
And if indeed the universe is akin to a grand thought or dream, that concept segues naturally into another, the role of the mind itself in the cosmos. We have touched on the possibility of a cosmic designer or programmer, an intelligence behind the scenes. But what of the intelligence within the scene, within the universe? We ourselves are conscious, and perhaps other beings scattered among the stars are as well. Could it be that consciousness is not just an accidental byproduct of the universe, but a fundamental aspect of it, as critical as space, time, matter, or information? With this question illuminating our path, we drift gently into contemplating the idea of cosmic consciousness, the mysterious emergence of awareness and its place in the grand tapestry of existence. Awareness, that flicker of light inside our minds, the sense of I am, is one of the greatest mysteries of all. We have voyaged across the universe in our thoughts, but now we turn inward to the phenomenon that allows us to experience it in the first place. Here on a tiny blue world, consciousness blossomed after billions of years of cosmic evolution. The atoms forged in ancient stars came together to form living beings that could look up and marvel at the sky. In us, and perhaps in other creatures, on countless other worlds, the universe knows itself, if only in a limited way. This simple fact is at once profound and humbling. We are made of the universe, and now the universe, through us, can reflect on its own vastness. In the stillness of this moment, consider what it means for matter to become aware. Particles that once flew indifferent in the void now form neurons firing with thoughts and feelings. Somehow the cold, inanimate cosmos gave rise to warm sentience, the inner glow of understanding and experience. How does this happen? How can the same elementary ingredients that compose a rock or a star also compose a mind that ponders meaning, beauty, and mystery? It is as if the universe had a secret, latent potential that only reveals itself when arranged in just the right way. That potential is consciousness, and it feels almost magical, though it likely arises naturally from the laws of physics, at least in our current understanding. As we float in the darkness, the significance of consciousness in the cosmic story becomes clear. Without observers, would the grand show of colliding galaxies and exploding stars have any witness to give it meaning? There is a famous philosophical question. If a tree falls in a forest with no one to hear it, does it make a sound? One might extend that to, if a universe unfolds with no consciousness to behold it, does it truly exist in any meaningful way? Perhaps it does in a physical sense, but the presence of a conscious observer transforms cold processes into experience. We do not know how many eyes or minds are out there among the stars, but we know of at least our own. For now, a tiny sliver of the cosmos, here on Earth, is awake and aware, gazing out into the rest. We have long searched for others, scanning the sky for signals, straining to hear a cosmic echo of another mind. So far,
the universe has been quiet, or our methods too limited to catch the whispers that might be there. It could be that life is incredibly rare, or that intelligent civilizations are separated by vast gulfs of time and space. Perhaps they are like lone fireflies on distant hills, too far apart to see each other's glow. It's possible some have advanced so far that they no longer send out obvious signals at all. One might imagine such beings constructing immense megastructures around their home stars, cosmic lattices or shells to capture starlight, causing their suns to dim or flicker in peculiar patterns. If we ever noticed such a pattern, it could be a quiet sign of intelligence, a gentle flicker that whispers, "We are here." So far, only tantalizing hints have teased us, nothing certain, and so the cosmic silence persists. And yet, it is hard to believe that in all this immensity, we are truly alone. Given billions of galaxies, with billions of stars and untold planets, the cosmos seems fertile for myriad experiments in life and mind. Perhaps even now, on a planet circling some tranquil star in a far-off galaxy, there are beings with their own sense of self, wondering if they too are alone in the universe. The thought that other consciousness might exist brings a gentle feeling of companionship across the void. We might never meet those distant minds, but knowing they could be out there makes the universe feel less empty. In a way, every conscious creature, wherever it arises, is like a candle lit in the darkness, small and fragile, but casting light and warmth around it. And collectively, if there are many such candles, they could illuminate the cosmos. Maybe one day, far in the future, those lights will connect, as technology or some transcendent evolution links minds across space, creating a network of awareness as vast as the galaxy itself. This is a speculative dream, but a peaceful one. A cosmos filled with understanding, different voices joining in a grand harmony of mind. Even if humanity stands alone for now, we represent consciousness on behalf of our galaxy. When we send out probes or messages into space, it is like the Milky Way itself sending out a greeting, because we are part of the Milky Way. Our achievements, our art and science, our music and our curiosity are expressions of the cosmos through one of its living components. We often think of ourselves as separate from the universe, tiny creatures clinging to a rock in space. But we are not separate. We are the universe, in the form of human beings, contemplating itself. The iron in our blood, the calcium in our bones, the water that fills our cells, these were forged in long-dead stars. We truly are made of stardust. And so, when our minds reflect on the stars, it is literally star stuff observing star stuff, a loop of cosmic self-recognition. A star, billions of miles away, shines its light for eons, and eventually that light nurtured life on Earth, which evolved eyes to see the star and brains to wonder about it. In that sense, the universe has arranged for a part of itself to see itself, to marvel at its own grandeur. This realization carries a comforting sense of belonging. We are not interlopers in the cosmos. We are its natural product, as integral to it as galaxies and nebulas and atoms. In fact, one might say the emergence of life and consciousness was a latent potential in the universe from the very beginning. Just as a seed contains the possibility of a tree, the universe contained the possibility of consciousness. It took time, billions of years, and myriad complex steps. But here we are, the outcome of that cosmic unfolding. And maybe elsewhere, other seeds have bloomed or will bloom. The universe may be sprinkled with these rare flowers of awareness, each one unique and precious. Some philosophers and scientists have gone further, suggesting that consciousness might be a fundamental aspect of reality, not just an accidental byproduct. They wonder if perhaps even simple particles carry a tiny glimmer of experience, an idea called panpsychism. If that were true, then in some unimaginably modest way, the whole universe would be suffused with a kind of proto-consciousness, which only shines brightly when arranged in particular ways, such as in a brain. It's a controversial idea and far from proven, but it speaks to an intuition that awareness might be deeply woven into the fabric of existence, rather than tacked on as an afterthought. At the intersection of quantum physics and consciousness, there are puzzling hints of a connection. In the quantum realm, as we mused earlier, particles exist in a haze of possibilities until something interacts with them, often described as an observation, causing the wave of possibilities to collapse into one outcome. Some interpretations of this strange behavior raise the question, does consciousness play a special role in deciding that outcome? Most scientists would say there's no evidence that a mind is needed. Any interaction will do. But the idea lingers that awareness might have a special place in the cosmic puzzle. It's a poetic thought. By the simple act of noticing a particle or a star or a sunset, perhaps a consciousness helps bring it into definite existence in the world of experience. Beyond physics, in the realm of subjective experience, consciousness is the canvas on which all of reality is painted for us. Without it, there would be no awareness of anything at all. No beauty or curiosity, no joy or sorrow. It is through consciousness that the universe becomes aware of beauty, such as the delicate glow of a nebula or the quiet shimmer of a distant galaxy. Recall the feelings that stir when a meteor streaks the sky, or when we see images of a far-off world. Awe, wonder, perhaps a profound sense of connection. Those feelings arise in consciousness and give the observed phenomenon a resonance beyond its physical existence. The cosmos inspires feelings in us, and those feelings are as real a part of the cosmos as the photons and planets, because they live within the minds of conscious beings. Some have described consciousness as the universe's way of experiencing itself, and in a very real sense it is. If the universe were a grand play, conscious beings are both the actors and the audience, bringing the performance to life by their participation and their observation. One can imagine that in the profound silence before life emerged, the universe was like a stage with no play, no eyes to see the curtains rise. Now, with life stirring in its nooks and crannies, the play is underway, and we are part of it. Is there a possibility that the universe as a whole has a kind of consciousness? This drifts into the realm of philosophy and metaphysics, but it's an intriguing idea. If one assembles enough minds or enough complexity, could a new, higher-level awareness emerge? We see hints of collective intelligence in things like ant colonies or the synchronized movements of flocks of birds and schools of fish. Some thinkers imagine that if civilizations across galaxies were to interconnect, sharing thoughts through communication networks, or maybe through future technologies, their combined knowledge and complexity might form something akin to a superintelligence, perhaps even transcending physical form eventually. Could the galaxy wake up in some distant epoch,
aware of itself as a single vast organism spread across spiral arms? Or is the universe already quietly aware in a way we cannot fathom, with our tiny spark of consciousness just a fragment of a greater cosmic mind? These ideas are deeply conjectural, but they expand our sense of belonging and connection. Whether or not the cosmos has its own grand consciousness, we tiny conscious parts feel a kinship with it. Lying under a sky full of stars can evoke a sense of unity. The boundaries between self and universe blur for a moment, and one feels woven into the fabric of all that is. Perhaps that feeling is not just an illusion of emotion, but a glimpse of a profound truth, that we are one with the cosmos. The atoms in our bodies, the thoughts in our minds, the light from those stars, all are interrelated in the grand scheme, all part of one existence. The role of consciousness in the universe's story is still unfolding. We are at an early chapter, where awareness is just beginning to fathom its own nature and its place in the cosmos. Through us, the universe has begun to contemplate questions about meaning and existence. It's a remarkable feedback loop. The universe created conditions for conscious life, and now conscious life is trying to understand the universe. In doing so, perhaps we change the universe just a little, by giving it self-reflection, by adding our choices and creativity into the mix, by potentially spreading life beyond our one small planet. All these thoughts about consciousness bring us to the threshold of something even more fundamental. We have explored the who and the how of existence, multiple universes, the nature of time, the fabric of reality, and the rise of awareness. Now, one last grand question emerges softly. Why is there something rather than nothing? Why does any of this exist at all? The cosmos, consciousness, or the laws that govern them? As we pose this question in the quiet of our minds, we enter the most profound mystery of all, one that may forever lie just beyond the reach of complete understanding. Why is there something rather than nothing? As our journey through thought and cosmos comes to its final chapter, we face this deepest of questions. All the stars, galaxies, particles, and even the abstract laws of nature. Why do they exist at all? In the silent darkness, we let the question echo without trying to answer it, like a sound ringing in an endless hall. Why is there something instead of an infinite void of nothingness? It's possible that our human minds, bound by cause and effect, aren't equipped to truly understand the answer, if there even is one. Every answer we could imagine leads to another question. If some creator or principle made the universe, what created that creator or principle? If an endless multiverse simply exists by its own nature, why does that nature exist? If nothingness is unstable and inevitably gives rise to something, why would that rule hold? We find ourselves looping in logic, much like the loops in time we pondered, or the nested simulations we imagined. Perhaps this ultimate mystery is not meant to be solved in the usual way. Instead, it stands as a gentle reminder of the limits of knowledge and the boundlessness of wonder. In a way, the very fact that we can ask the question is beautiful. It means we are here, that somethingness is our reality. If there truly were absolutely nothing, there would be no stars or galaxies, no earth or sky, no life or consciousness, to even pose the question. The simple act of wondering why we exist underscores that we do exist, as part of this magnificent tapestry.
Some thinkers point out that if nothing had been the case, none of this contemplation could happen. So the only reason the question occurs to us is because we already have the gift of existence. This is a version of the anthropic principle. The universe must have properties that allow observers to exist, otherwise no one would be around to notice. By extension, the fact that we find ourselves in a universe that permits something might be explanation enough. Not a satisfying answer in terms of cause and effect, but a recognition that in some sense existence just is, and non-existence holds no witness to question it. Maybe the universe exists simply because it can. Maybe existence is more natural than non-existence. After all, even what we call nothing in physics isn't truly empty. It's a simmering field of potential, capable of birthing particles and energy for brief moments. Perhaps true nothingness is unstable or impossible, and the stage of reality must always be occupied by something. Others have speculated that every possible reality exists in some form. One of those realities is an empty void with no stars. Another is a universe full of light and life. And only in the latter do beings arise to marvel at it. These are guesses, attempts to put boundaries around the unbounded. In the end, after all the theories and imaginings, we are left with a serene acceptance. There is something rather than nothing, and that fact alone is a source of wonder. Rather than being haunted by the absence of a final answer, we can find solace in the presence of the mystery. The unknown has a way of humbling us, but also of connecting us to something greater than ourselves. We stand here, small sentient beings in a vast and ancient cosmos, pondering the fact that there is a cosmos to ponder. There's a poetry in that recursion. As this thought settles in, we feel a gentle closure. We have wandered through cosmic expanses and ideas beyond the edge of reality, and now we return to a simple truth. We are here, a part of all that is. In the grand scheme, our lives are fleeting flickers, but they are embedded in this endless tapestry of existence. Every atom in our body, every thought in our mind, is a note in the cosmic symphony that has been playing since the dawn of time. We may not know who composed the music or why it plays, but we can still close our eyes and lose ourselves in its beauty. Now the journey winds down. The stars above continue to shimmer in their silent patterns. Galaxies continue their slow dance, and somewhere in the distance new universes might even be taking shape, while old ones fade away. These processes will go on, with or without our awareness. An endless ballet of creation, transformation, and repose. We, having travelled so far in our imagination, come back to the present moment, to the gentle rhythm of our breath and the beating of our heart, which remind us that we are here, now. In this moment, we embrace stillness. The questions, the theories, the grand cosmic dramas, all drift quietly to the background, like leaves on a pond settling to the bottom. A deep peace comes to the forefront. It is the peace of knowing that it's all right not to have all the answers. It's the peace that comes from feeling at home in the universe, even with all its enigmas. We can simply be, as the cosmos simply is. The night is tranquil and vast around us. Imagining ourselves lying under the open sky, we feel the cool breath of the dark and the gentle pull of the earth. Above, ancient starlight falls quietly, having travelled eons just to reach this place and time. We are cradled by infinity, yet we feel secure, like a child held in loving arms. The universe that made us is all around us and within us. In that understanding, there is a profound comfort.
Slowly, our cosmic tale comes to a close, not with a sharp end, but with a slow fading of words, like the sun dipping below the horizon. The awe remains, the mystery endures, but now is the time for rest. The mind, filled with stars and wonders, can gently let go and drift, like a spaceship turning off its engines to glide silently through the void. There is nothing more we need to do, nowhere else we need to go in this moment. The exploration pauses, and in that pause we find rest. As we surrender to the quiet of the night, it's as if the universe itself watches over us. Each star might be seen as a distant lantern in the dark, a tiny beacon reminding us that light persists out there. The cosmic ocean of which we are a part holds us afloat in its dark, gentle waters. We can trust this vastness. It has given birth to us and carried us through time. Finally, as our thoughts grow as faint as faraway galaxies, we slip into a state of pure being. In this calm, perhaps we feel a connection to everything we've pondered. We are one with the stars, one with time and eternity, one with the great mystery. The boundary between the self and the cosmos softens. We rest in the knowledge that we belong, that we always have, woven into the fabric of existence from the beginning of time. In the quiet darkness, a last image flickers in the mind, a universe dreaming of itself, stars and galaxies drifting by like thoughts, and within one of those galaxies, on a small blue world, a spark of consciousness gently falls asleep under an endless sky. The journey has been wondrous, and now the journey becomes a dream. In that dream, we remain, cradled by the cosmos, safe and small, at peace with the deep and beautiful unknown.